হ্যাঁ দিদি। ও দিদি, ভিডিও তো আমার এখান থেকে করলে ইয়েই কেটে যাবে আমার মনে হয়, মুশকিল হয়ে যাবে আমার। এমনি ব্যান্ডউইথের কেউই তো দেখছি না। ম্যাডাম তো রয়েছেন, ম্যাডামকে বলো না, তুমি একটা ইয়ে করো না, যে মেসেজ করে দাও না আমার কথা। হ্যাঁ, ম্যাডাম আমার কথা শুনে গেছে।
Devanduti, please on your video. Devanduti,
Yes, ma'am.
please keep your video on
Okay, ma'am.
because I will be off for some time.
Hello. Hello.
Welcome, Professor Hajra.
হ্যাঁ, এখনো দেখা যাচ্ছে না সবাইকে। হ্যাঁ, ঠিক আছে।
ঠিক আছে, it's all right.
আমি আমি আমার শব্দ শোনা যাচ্ছে না? আমি এটা
No,
লাগাবো।
no, it's all right.
মাইক্রোফোন লাগাবো না ইট ইজ ওকে?
It's clear.
ক্লিয়ার? ওকে,
No need to just for additional speaker, I think.
ওকে।
Okay.
জাস্ট একবার দেখে নিই এটা শেয়ারিংটা নাকি না দেখার সময় আছে?
We have another 7 minutes to speak.
5 minutes. 2 minutes will be fine. Just
Okay.
to share here. Is it okay?
Yes. It's okay.
Huh?
It's working.
Fine. Okay. Great. So I'll stop sharing.
Okay.
One second.
Can you hear me?
Yes, yes.
Okay.
I think I'm just let me check whether I'm getting it by this thing or not. Microphone.
Ma'am, can you hear me, ma'am?
Yes. You're audible.
Okay, ma'am.
But you may close your video, Devaduti.
Devaduti, don't close. Yeah.
হ্যাঁ ইন্দ্রাণীদি, আমাকে শোনা যাচ্ছে তো? গার্গী বলছি।
Yes, yes, yes.
Yes.
তোমাকে শোনা যাচ্ছে।
Okay. Thank you.
Devaduti, can you
Yes,
hear me?
ma'am. Yes, ma'am.
Yeah, keep your video on.
Okay, ma'am.
Thank you.
It's on, ma'am, already. Ma'am. Ma'am, am I visible?
Yeah, I can see you.
You are.
Okay. But I can't see myself. I couldn't see myself.
See yourself, but we can see you.
Okay.
Let me try with the microphone whether it will take or not. I don't know.
Gargi?
No, it's not functioning.
Gargi, can you hear me?
Yes. Indradi.
Yeah, I got disconnected for some time.
Okay.
Just okay. Now I am in.
Okay, no problem.
Gargi, there's no screensaver.
Which? Making.
Yeah, something can be put in the computer screen.
System.
টা বাজলো কিন্তু Indrani ma'am.
Start. It's just
Yeah,
5.
yeah, it's just fine. Devrat can start.
Yeah.
Am I audible, Alodi?
Yes,
Hello?
perfectly.
You are on.
Okay. Okay, thank you, sir. Thank you, one and all, for giving me such an opportunity to welcome you on behalf of the Department of Botany and Geography of Shet Anantram Jaipuria College. I heartily welcome our administrator and our principal, sir, Dr. Ashok Mukhopadhyay, for their continuous support and help for organizing today's webinar. A warm welcome and heartfelt gratitude to the dignitary speakers, Dr. Sugato Hajra, Dr. Sanjeev Kumar Singh, and Dr. Scott A. Brown. I must solicit my gratitude and warm welcome for accepting our invitation and taking out time from your busy schedule. This is our immense happiness to be listening to you all in this August gathering. I welcome Dr. Radhanath Pain, Professor Nandita Chakraborty, Dr. Srimonti Chaudhuri, Dr. Indrani Dash, Professor Alo Guho, Dr. Nilashish Pal, Dr. Sudeshna Shao, Dr. Gargi Basu, Professor Oendrila Ghosh, Dr. Orpita Rakshit, Dr. Madhumita Mishra, Professor Tanima Dash, Professor Devoduti Mitra, Professor Gaurav Roy, and Professor Sharmi Bhattacharya, and all our beloved colleagues, students, and non-teaching staff. They all are always there before and behind the screen and actively did their all duties with a never-ending smile. I also extend my warm welcome to Dr. Indrani Dash ma'am for undertaking all the painstaking work to organize the program from its day. And last but not least, you dear all participants from across crowd, I thank them all for sharing their valuable time and being a part of this endeavor. Please remain connected until the end and help us to make the program a grand success. Now I call upon Professor Alo Guho to continue with the proceedings of the session. And thank you for listening to me. Thank you. Thank you so much. Over to you, Alodi.
Thank you, Professor Debraj Roy. I am Alo Guho of St. Anandram Jaipuria College, Kolkata. A very good evening to everyone present here, to our honorable principal, sir, our respected administrator, sir, our distinguished speakers, Dr. Scott A. Braun, Hajra, Dr. Sanjeev Kumar Singh, all faculty members and staff of our institution, faculty members of various other colleges and universities attending this webinar. the internal quality assurance cell of our college, the members of the organizing committee and technical assistance team, and everyone involved in this webinar. And last but not the least, a very good evening to our dear students near and far. This webinar is divided into 3 technical sessions. The speaker for the technical session is Dr. Shubhata Hajra. His topic is haunted by speaker of technical session 2, Dr. His presentation title is Applications of a numerical weather prediction model for tropical cyclone. The speaker of technical session 3 is Dr. Scott A. Braun. His topic is tropical cyclone. We now begin the technical session 1 of this webinar by introducing our first speaker, Dr. Shubhata Hajra. Dr. Professor of Zone Management and former director of the School of Oceanographic Studies of Jadavpur University, West Bengal, India. He has done pioneering research on the Sundarbans, climate change, and biophysical impacts. He has led several national and international level research projects on the Sundarbans and coastal oceans and has more than 100 international publications, edited volumes, monographs to his credit. During his academic tenure of 30 years, he has mentored over 30 PhD students. Dr. Hajra has been a member of the Indian Antarctic Expedition in the year 1996-97. He has been awarded the Corporate and was a recipient of the gold medal from Asiatic Society. He is also an expert member of Coastal Zone Management Authority of West Bengal. I now have the pleasure to welcome and invite our honorable speaker, Dr. Shubhata Hajra, to enlighten and inform us about the Sundarbans through his very relevant and absorbing topic, haunted by hurricanes and chased by cyclones, the Sundarban Delta in siege. Thank you all. Over to you, Dr. Hajra. Please join us, sir.
Yeah, good afternoon, everybody. And I'll request everybody to keep their microphones muted while the session is on. And you can put on your microphone again when you want to speak. And let me start sharing my screen. Let me see how it comes. No, it is not. Can you see?
So actually, it's showing that you have low bandwidth conditions in your local computer. From where you are sharing?
Where am I sharing? It is showing a low bandwidth connection.
Yes. Yes.
Shall I start again, or is it okay now? No.
No.
Hello, is it coming or not?
No. No. No.
No.
Okay, just is it coming? No.
No, sir.
So let me. Showing low bandwidth again.
Yes.
So I don't think this problem. Let me check with my. I'll shift the connection. So
Yes.
meanwhile, would you just ask somebody, the next speaker, to speak on so that I can get the lines through?
Indranidhi, can we do that?
The next speaker hasn't joined us yet, I think.
Oh, I see. I see.
No,
Let
he is there. He is there.
me share. It's not coming into sharing. Unable to share this. See it? No.
No, sir.
But we just said and it was functioning well. But suddenly, okay, just let me have some minutes to change the connection.
Okay. Okay, I'm sharing my screen. You show me what message is coming. Okay, sir.
Yes, yes. Can I present the articles right now?
Yeah, shall I send it by mail?
No, sir. No, not your presentation. I'm talking about the articles that was planned. Now it's
I'm
working, sir.
sharing one page.
Is it working? Is
Are
it
you
working?
sharing a screen, sir?
Yeah,
I'm sharing one page. One page.
I'm
It
sharing the
again,
screen.
yes, a screen is showing. Blue screen computer.
No.
That it is showing.
No, sir. No, sir.
Shared.
भैया जाओ ना तुम लोग, हम आ रहे थोड़ा देर बाद आए। अरे हाँ,
Can you
इसको
see
लेके
it?
जाओ।
No, sir.
नो सर, स्क्रीन नहीं आ रहा है सर का, बार बार अटक जा रहा है।
Yesterday when we tested, it was okay, Gargi.
Yes, it was okay. Actually, it's the messages. One message is coming that sir's local computer has low bandwidth connection. That's why the video is not running.
Can I do one
We
thing?
need to restart the internet connection once again, I guess. If sir can just restart the internet, maybe sometimes.
Yes, now it's coming. Now it's coming.
Coming? Okay.
Yes.
Yes, sir. It's showing that you're sharing.
So the video is taking too much time, I think. Could you see the screen now? No.
No, not right now. It was coming, but right now nothing.
I'm trying to shift the connection. Disconnect করছি।
Morning, it was absolutely fine.
I think because of poor network connections now.
And sir tried 5 minutes before the program, right? Then also it was okay.
Right. Shall we try? No, it is not connected. Indrani, can you hear me?
Yes, we can hear you, sir, but can't see you.
Let me see. I have taken from the mobile. Let me see how it comes. I'm closing it now. Just I'll reconnect.
Gargi? Hello? Gargi, can you hear me? Gargi? Gargi?
Yes, Indranidhi.
He can send you the PPT so that you can display that PPT and he can talk.
Okay, okay.
Okay, you just
Okay.
tell him your email ID so that he can send you that PPT.
Okay, I'm sending my mail ID to you and you then forward it. Okay.
Okay. Please. Hello? Hello? Hello?
Yes, ma'am.
We can start the e-publication session. It will take a few 5 minutes only. So within
Thinking about
yeah,
that.
we can.
Now?
Yeah, you can start.
Okay, I'll start. Just give me a few moments, ma'am.
Okay.
Is it showing on the screen like I'm presenting?
Yes, Alodi, yes, it's coming.
I'll start the. This is a presentation of slideshow of selected articles submitted by students. These articles will be compiled in an e-publication subsequently. And let me begin the presentation of articles. The first article is titled Changing Scenario of Land Use and Land Cover in East Kolkata Wetlands in the Aftermath of Amphan Cyclone Using Remote Sensing and GIS, a comparative study. It has been compiled by Shayoni Shaha, MPhil scholar, School of Oceanographic Studies, Jadavpur University, Kolkata, in collaboration with Dr. Rakhi Soren, Assistant Professor, School of Oceanographic Studies, Jadavpur University, Kolkata. It has its keynotes are introduction, a detailed description about Amphan cyclone, and a comparative scenario of land use and land cover. Please, someone is like, I'll start again. Something is wrong, like someone interfered, I think. Now, is it visible? Is the screen visible?
Yes, visible.
There is something like someone, these marks are coming. Let me try once more. So this was the first article. The second article hanging. This was the first article. The second article is titled Use of Artificial Intelligence in Cyclone Forecasting, prepared by Sarthak Boshak, Semester 5 student, Department of Zoology, St. Anandram, Jaipuria College. We know that machine learning has been incorporated in our new education policy 2020. So this article would be a fascinating study. The third article is titled Cyclone and Related Issues, prepared by Abhilasha Ganguly, Semester 3 student, Department of Zoology, St. Anandram, Jaipuria College. The next article is titled Cyclone, a Source of Massive Destruction, prepared by Pritam Roy Chaudhuri, Department of Chemistry, St. Anandram, Jaipuria College. He has given a list of tropical cyclones that affected West Bengal starting from 1970 to the current Amphan cyclone in 2020. The next article is titled Weather Disturbances, Atmospheric Disturbance Leading to Cyclonic Issues. I don't know why people are like, there is interference. Should I approve or decline this? Kaustav Roy is requesting to
Decline it.
So this article is titled Weather Disturbances, Atmospheric Disturbance Leading to Cyclonic Issues, prepared by Shweta Kesharwani, Semester 5 student of St. Anandram, Jaipuria College. She has stressed upon two major cyclones, Cyclone Dorian and Cyclone Fani. Cyclone Dorian, as far as you know, it was a Category 5 hurricane which attacked and ravaged the Bahamas, while Cyclone Fani happened just a year before. The next article is titled Economic Impacts of Cyclones, prepared by Adrija Ghosh Dastidar of St. Anandram, Jaipuria College. The next article is Bhola the Destructive, prepared by Shikha Singh, Semester 5 student of St. Anandram, Jaipuria College. She has given an introduction to cyclones with special reference to Bhola. Bhola was in fact a deadly, devastating tropical cyclone that struck the Bangladesh on November 11th and 12th of 1970. It remains one of the deadliest tropical cyclones in which nearly 3 lakh people lost their lives, mostly due to the storm surge that followed, wiping out villages and flooding large areas. The next article is titled Cyclone and Related Issues, prepared by Shreya Sharkar of St. Anandram, Jaipuria College. She has given key notes to introduction of cyclones, types of cyclones, names in different parts of the world, formation, components, categories, examples. I need to mention that weather forecasters give each tropical cyclone a name to avoid confusion. Naming storms helps in quick identification of storms in warning messages because names can be easily remembered than numbers and technical terms. The next article is titled The Historic Cyclones and India, prepared by Neha Gachwi, a Semester 5 student of St. Anandram, Jaipuria College. She has mentioned the structural and non-structural measures needed to combat tropical cyclones, the damage caused by tropical cyclones. The next article is Cyclone and its related issues, prepared by Sarifa Khatun, MSc student, Department of Geography, West Bengal State University. She has given keynotes as to introduction to atmospheric hazard and cyclones in particular, concept of a cyclone, characteristics, formation, types, and cyclone-prone states in India. So this is the end of the slideshow. I would now return to the meeting. Has sir got his sharing ready?
He has sent the mail to Gargi. Gargi, please check.
Today there's lot of connectivity issues going on here.
I have not yet received the mail from sir.
Okay, I think he has sent it to me. I think he has sent it to me. I will forward it. Gargi, just wait.
Okay.
Gargi, please check. It is sent. Did you get
Okay.
it?
Just a minute. Not yet.
Yeah.
Indranidhi, you can share from your system also.
I can't because network is slow here. Even I am having some problem. Just
Okay.
networking problem.
Okay, I have received just.
I have already. You have
Yes,
received?
yes, just received. Just received. Just a minute. Let me download.
Gargi, you could download the files.
Yes, I have download and I'm just opening. Just a minute. Give me
Okay.
a minute. Okay.
Sir has joined? No?
No, he is not there.
Okay. Okay.
Yes, he has joined right now.
Hello?
Ah,
Please note one article is left, Cyclone-Amphan and its effect on economy. That student wrote me that her paper was not mentioned there. You please note it down.
Selected, Indranidhi? Is it the selected one?
I think it was selected one. Just please check it. She is from Bethune College.
what's her name, ma'am?
I didn't ask. Okay, I'll write in.
Because not all articles were displayed, only selected articles were displayed.
Riddhi Mukherjee from
No,
Bethune
ma'am.
College.
Her article maybe wasn't selected.
Okay.
Not in this list.
হ্যালো হ্যাঁ পাঠিয়ে দিও হ্যাঁ 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 ওকে হ্যালো হ্যাঁ 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 আচ্ছা আচ্ছা ঠিক আছে আচ্ছা আচ্ছা ওকে ওকে কি নামে আছে আচ্ছা আমি গার্গিকে বলে দিচ্ছি ওকে গার্গি গার্গি
Hmm.
hear me Professor Hazra is trying to connect you. You please respond
Okay.
from another computer
Okay.
and check the sound system and audio system, okay? So that he
Okay.
can talk.
Okay. I think sir is there.
Okay, but we can't hear him. Something going wrong with his audio system, or you please check whether muted or unmuted.
No, nothing is showing me.
হ্যালো ও অ্যাপ্রুভ কি নামে আছে ওটা অ্যাপ্রুভ করতে হবে না ও তো বলছে স্যার এখনো আসেনি আচ্ছা আচ্ছা ওকে Okay, okay, okay. Gargi, please check some. He is trying from another computer. Some Hazra, you please accept.
Sure, nothing is coming in my system.
Oh, just you have to just keep him as a presenter, not as viewer. Okay.
Yes, I did that.
Okay. Yeah, she has done.
Hello. Can you hear me and see me?
Yes, yes, sir. We can hear you.
Great. Daddy, would or Gargi, will you show that PDF that I
Yes.
was showing?
Gargi,
Yes,
Gargi,
yes.
please start. Okay.
Yes. Now it's coming.
Okay, great.
Sir, please start.
This will not have animations. This thing, if I can, but so all glad that I could come back and you. It's a picture that is actually not supporting like that. It is hunted by the hurricanes and chased by from person's perspective, not from the atmospheric scientist. Because now we have our eyes and ears on the ocean and the sky, but we can go to the next slide. Can you go down? Next one, yeah. The delta, as you can see, the great Ganges Brahmaputra delta, and we are in the this part, western part of the delta. So this part, along with Bangladesh, has been devastated by cyclones from the very ancient times. And if you just recall the last decade, that you can remember the names like Aila, Giri, Hane, Neelam, Filene, Hudhud, Komen, Titli, Fani, and Bulbul, and Amphan, which have struck the delta, or it has just missed it. It has whisked away from sight, and we have shied relief, shy of relief. So I think that this is a delta which is chased by the cyclone and haunted by the hurricanes. Because the name cyclone, can you go to the next one, please? Next slide, please. Then scroll down. Yeah. It was the Hooghly River hurricane that we can have earliest record, that on October 11 in Gregorian calendar it is 30th September. But well, that was the first record. Yes, fine. Made a landfall in the Ganges River Delta with reported 381 millimeter rain falling in 6 hours period. You can imagine the nature of flooding. And the storm tracked approximately 330 kilometers inside. And it was a huge storm surge, killing about 3 lakhs, means 300,000 to 350,000 people. That was the earliest record of cyclone we have in this delta. The next slide, please. This one, yeah, this one. Actually, I was thinking of talking about Piddington in a length, but we have very short time now. Henry Piddington was a mariner, East India Company, and he came to in charge of meteorology, and he wrote a lot of books. And he first coined the term cyclone for a spiraling snake-like wind coming from the sea, sitting on the river Matla. And he wrote a book on that. It is the law of the storms. And while the port being built, was he went on building the Paddington was warning that, well, it will be destroyed by cyclone. So it happened just like that. Fort Canning was destroyed in 1867 by a cyclone, and this in the left-hand corner. The kerosene lamp we generally know as hurricane, which will not be extinguished by the strong or storms like hurricanes, was introduced in India. Next, please. So people are curious, and also our students who are curious that what actually prompts the cyclones to form. It is generally known that the sea surface temperature, if it is 26.5 degrees centigrade, uh, very favorable for formation of cyclone. Unfortunately, Bay of Bengal for 5 months to 6 months, it is warmer than 26.5 degrees centigrade. So it remains a question that whether the cyclones will continue forming in Bay of Bengal. But it's not like that, because you need a deep, warm ocean below the hot spots in the ocean uh, to supply the fuel of the engine, heat engine. So you need a very deep, warm ocean, maybe 200 meters deep, up to 200 meters deep, it should be warm. And a pre-existing circulation is needed above the hotspot, aiding the transfer of heat from water as water vapor and to the ocean to atmosphere, creating a buoyant, warmer core of the rising air of low pressure and low vertical wind shear in the troposphere. That means it should be easily going up. The wind should not be very strong in the upper, middle or upper tropospheric level. It should be less than 10 meters per second. And then rapid cooling with the rise, so that it's a deep convection clouds and cumulonimbus clouds to form, and relatively humid, important criteria, humid middle atmospheric level, to prevent the formation of the downdraft, that is a collapse of the deep convection. Because if dry air comes from outside to this cell, this will evaporate the moisture and the circulation will break down. So this is it is a very rare situation that all these conditions, 6 to 7 conditions, are met. However, we are observing that in I have just described, the northern Bay of Bengal is becoming warmer, and surface temperature, not sea surface temperature, is quite warm. That means the heat engine is now ready, and probably Bay of Bengal is facing more and more cyclone because of its heat content. Next, please. Probably this thing animation. Oh no. So this was the last cyclone we have seen, and from this Earth observation system that my next speakers will be talking about at length, we have observed the Amphan to develop, and we have issued warning from the meteorology that Amphan was a deep depression that is 50 to 62 kilometer per hour speed on 16th May. It developed in storm 16th May again, that is IMD that I'm talking about, and severe cyclone storm on 17th May. So gradually it is intensifying. Then in the very severe cyclonic storm of 118 to 165 kilometer per hour on 17th May, and in 18th May, early hours, it was a extremely severe cyclonic storm, and then it is a super cyclonic storm. So probably this is after 1999, we are observing a formation of a super cyclonic core of a storm, 221 kilometer and above in May 2020, 18th May. Then some process of, you may say, eye wall replacement took place. So after the intensification, it is the declining of the intensity. So it went down to a extremely severe cyclonic storms, and then finally made a landfall on Chagor Island as a very severe cyclonic storm at 3:30 p.m. Wind speed was 55 to 165 kilometer. So you can see that how the quickly the cyclones intensified. It's called rapid intensification. Then it can sometimes degenerate because the extremely low pressure eye is protected by from the outside higher pressure area through an eye wall. It's storm clouds and other things. So these actually prevent the eye to degenerate. But sometimes this eye wall break and the convection is weakened. Next, please. Next, please. So we will not see these. Animation. We will go to the. These are our Indian meteorological satellites that through which we generally observe and analyze the different levels of the clouds and the atmosphere as well as sea states. So I think now we are equipped to chase the hurricane, but how to assess the people who are chased by the cyclone, I'll go into that. Next, please. The international satellites, geostationary as well as polar orbiting satellites. I think my next speakers will be talking more about these things. So I'll skip it. Next, please. Next. Yeah, so this is the development of cyclones that I was discussing. And we have classification that is the warmest low wind shear, and it developed into extremely severe cyclonic storms with 933 hectopascal. So it is an extremely severe cyclonic storm coming to the delta. Next. Next. Yeah. At the time of landfall, major question other than the high wind speed destroying all of the buildings. Before that, just no, not this, not this. Just above it, above it. Please go to the previous one. Previous. Yeah, previous one. Previous, please. Previous. Yeah, this one. So it was the storm surge. No, no, not this. The surge one. The inquest. The previous one, please. previous. Aage, please keep it here. Please, my God. Please go to the inquest. Yeah, please keep it here. Here. So this was a computed storm surge. I mean, what is storm surge? You may see I had an animation. I'm unable to show it. If it permits, then I can show later. Uh, you can see these are the inundation by an approaching wave from the ocean. This is the biggest killer of any kind of cyclone because the water can flood anything. It can be from 2 meter, means 4 feet, 6 meter to 9 meter even at the time of Orissa cyclone. And we have report of had storm surge in the delta from the past. But 9 meter cyclone we have storm surge we have seen for Orissa super cyclone known as Kolinga super cyclone. However, you can see that the storm surge formation is very important. Uh, it is very important because the storm surge, whether it will be inundated, will be dependent upon a lot of factors. And these I'll come to my main question of today's discussion, that why Aila, being a smaller and weaker storm of less than 120 kilometers speed per hour, could generate a bigger storm surge, inundating a much bigger area in Sundarban compared to Amphan, which was a much stronger cyclone with a bigger predicted storm surge height of 4.6 meter above the above the tide level, uh, which would have destroyed up to Calcutta by storm surge, because Calcutta's height is only 7 meter from the sea level. So if it is tidal height is 5 meter plus 4 meter means 9 meter water, then it could have been entire destruction of the delta. However, thank something, it didn't like that. So I'll explore the situation that how it might not have happened and what actually prevented it formation of this storm surge. So next, please. Yeah, next, please. Yeah. So this was our first level observation by Shamanta, one of my students. Mm, uh, the map areas. Very interesting. The saga and what the follow there was inundation in the marginal areas to the, and there are inundation, and the northern part, which is the blue line area, there are big inundation. So in the this is the Sundarban biosphere area, other than the Sundarban forest area in the eastern side. So this we become curious about the pattern of inundation, which was again observed from the radar satellite data, that is the Sentinel data that we have used. Next, next please. Yes, so then we calculated the at different blocks of Sundarban, what was the percentage of inundation. So Shagor was showing the maximum inundation, Pathar Pratima by next, and then Mothurapur 2, and lowest was Haro. However, then next please. Next slide, please. Yes. When we tried total inundation area to saltwater inundation, rainwater inundation, using the creeks and the broken embankment, then taking telephonic confirmations from our different people who are working in the delta in different villages, then we could decipher that major part of this inundation by Amphan was by rainwater, which is a very heavy rain, and the saltwater inundation was very high in Pathor Protima, whereas compared to Shagor, which is a big inundation, Shagor Island, the saltwater inundation 200 hectares, while the saltwater rainwater inundation was around 4,000, above 4,000 hectares. So this was the pattern of inundation. So it was not actually the inundation was not actually by the storm surge, but actually by the heavy rainfall and the very high wind. The devastation was there, and around $14 billion of total devastation, and more than 100 deaths were reported from the delta, but it was much smaller. The death and the damage was much smaller than that 3 lakhs in 1737, because now we have our Earth observation system, and we could warn, we could evacuate the people from the vulnerable areas of Pathor Pratima, Shagor, or Mosuni Island, or from G plot. So next. So this was a fantastic. I mean, you can see the level of inundation that we photograph of, actually supplied by to me by one of my friends, Subhash Acharya. Next, please. We are discussing the storm surge. It is not only the cyclonic wind, but the storm surge, that is the flood of water which enters with the storms and flood the area, which makes the real killing for a cyclone. So we also tried to assess the damage of the mangrove forest with, uh, uh, with the SAR. Uh, I mean, it is a Sentinel data of pre-Amphan comparing with post-Amphan of 20th May, and we have used a formula proposed by Philgrius in 2019 paper, and we have taken the difference like NDVI. This is a index of mangrove health change index normalized ratio procedure bands. They have named it like that. Whereas what uh, VV and VH and as well as the summation was made ratio, but we could ascertain that there's a very strong destruction or the reduction of health in the mangrove forest area. The one that's the red are showing the high inundation. Yes, blue green color are showing low damage. So the low damages were only 36% of the 2100 square kilometer forest area, whereas 41% showing a moderate damage and 23% was showing a high damage. So again, we are not only chasing the cyclone from the satellites and our aircrafts, but we can actually assess the damage by cyclones now from the satellite data. Next, please. This is the cyclone that I want to compare. I was talking about a very low one cyclone of Aila, which actually devastated the delta in 2009. It is again, I mean, pre-monsoon cyclone season cyclone that is again in May. That is 20th May was Amphan and 25th was Aila, and it went straight north. It didn't actually bend like cedar or phony or bulbul, but it went straight like that, which like Amphan more or less, and but the intensity was much less. But the very important difference is that as this Amphan storm passed over the delta by 5 to 6 hours, Aila continued its intensity more than 50 hours after landfall. That was the biggest difference it could make, and probably it was responsible. You can say it like Dorian. It was a slow cyclone. It was a slow moving cyclone when it came to the land, and even after landfall, it kept its intensity. So please go to the next slide. Next, please. So is it a kind of brown ocean effect that we can inquire, where actually the land with lot of moisture and evaporation of moisture is behaving as if it is a brown ocean and can supply the fuel of the hurricane, of the cyclone, so that it is actually Ayla traveled up to Darjeeling and Sikkim, and in Sikkim 25 people were killed by the uh, snowslide because of Amphan heat. So that was a terrible thing with a 118 km per hour speed cyclone, where 165 kilometers of Amphan, it couldn't make the damage like that or inundation like that. So that was the formation of the cyclone as observed from our Indian satellite. Next. So cyclone genesis is favored in Ayla. Again, this was only 1 degree centigrade above normal. This kind of temperature now we get every day now in Bay of Bengal. It was very uncommon in 2009, and the wind speed was relatively stronger and southeast sector. So there was a southerly surge of the monsoon current also. Next, please. The impact of Ayla was very. There is a storm surge of 2 to 3 meter. Actually, in Amphan, we didn't get that kind of high storm surge tide, but in Ayla we got it, received it, and entirely it could flooded the Sundarban and inundated by 6 meter of water as per the media reports. And according to the media report, the state chief secretary put the number of storm affected people to be 2.2 million, and more than 61 houses collapsed and 132,000 partially damaged. So it has a very heavy impact. And now we'll compare the inundation by Ayla and Amphan. Next, please. Yeah, you can see the left one is the Amphan inundation at the village level. You can see there are 4-5 sea-facing villages of Shagor. The blue one in Mousuni Island is Baliara. That is the Bokkali area in Pathor Pratima, Chiplot. There is Buraburi Tot and other areas. And the inside part of the Sandesh Khali 1, 2. And it can go up to North 24 Parganas, Najat and other areas. But it with the Ayla inundation surge of 2 to 3 meter and predicted surge height of 4 to 6 meter above the astronomical, created a lesser inundation. Why? I think this is a question to explore. Next, please. Next, please. Yeah, this is the surge is actually dependent on the storm approach angle to the coastline as well as Ekman's transport. So here I add a little. That is actually the direction is not always the surge direction. The surge can be transported with an angle to the wind. So if the wind approaches, the cyclone approaches, it is actually the right hand side because of the Coriolis force that the storm progress. It can be as high as 45 degree, even up to 90 degree at some point at level, but at the shallow water level it is hardly 20 to 25 degree. So then the surge will actually not enter Sundarban if the storm approaches as it has approached for this thing, for Amphan. Then the tidal condition, while at the time of landfall, is very important because this storm surge, say this much above the low tide level, above the high tide level, will create the storm tide level up to this and will flood. But if this level, the high tide level, actually not high tide but a low tide, so if the storm hits at the time of low tide, so even this 3 meter will not cause your breach of embankment will not enter into the land. So the time of landfall of the cyclone vis-a-vis the tidal condition, whether it was a high or low condition, it is important. And the storm intensity, the storm speed, the storm size, the pressure at the eye are important, but not as high as the bathymetry of the rivers inside the delta through which the storm surge will progress, and the coastal slope as well as the topography. And these are the gray areas for the delta that I'll come into it. So these are the factors that actually can generate or not generate a significant storm surge. Next, please. Yeah. Another very important point can be the wind direction as the time of Amphan. So it was a Sagar Island observation that while during the landfall, the wind was blowing from northeast, that is around 40 degrees. So if the wind blows from northeast, your surge will not enter because the surge is coming from the south. But very interestingly, after the landfall, if the wind moved to the west quadrant, that is 260 degrees. Now it is blowing from the west. So this will drive the surge again towards the forest area, and it will not bring the surge to the habitation area, which is lying at the north of the storm. So I think this is very interesting observation that the wind can also play a trick at the time of landfall, which may aid the surge to progress to the continental side or through the rivers, or actually can move the surge along the coast and can actually inundate the Sundarban forest area. Next. So probably these two things together we have seen at the time of Ayla also, because Ayla, the wind also before landfall was blowing from 50 degrees, then suddenly it changed to 300 degrees. So it was blowing from the northwest. But the point in Ayla was not the wind direction of the storm. Actually, Amphan crossed the Sundarban within 6 hours, the delta. But Ayla was stationary with higher velocities of storms, wind speed, up to the 15 hours. So it has seen two tidal cycles. Next. So here comes another important factor which actually created the surge during Ayla, but not that high surge during Amphan. That is, the clinching point is that when Amphan struck at 3:30 p.m. at Sagar Island, the lowest low tide was 2.46 p.m., that is, say around 3, was the lowest low tide condition. So even if above 1.6 meter, we had a 3-meter high surge, the total storm tide will be 4.6 meter, which is less than the normal high tide we will face here. So actually, Amphan, in spite of being a bigger storm, a stronger storm, could not create a strong storm surge because of it actually struck at the low tide condition. It passed before the next high tide came up, but some amount of water was there. So at the time of the next high tide, around 8:30 p.m., some of the areas observed that the tide is entering to their island, like Sandesh Khali or Bali, or even in Ramganga, these areas. So with 7:30 onwards, they were observing the tide is entering in their village. So that was because the next high tide was carrying the some amount of remaining surge. Otherwise, this surge was carried to the west. So it didn't go to strike the Sundarban, habitation area. And the next thing also for Isla, you can see the difference. Go to the next slide, please. Yeah. So Isla, in 25th May, when it struck landfall at 1:30 p.m. So around 10 p.m. We had a high tide of 5.46 meter. So it was a mid tide condition closer to the high tide, where reducing high tide, it is falling to the next low tide will be in 4:26, 4:30 p.m. But by that, it has got significant high tide situation plus a storm surge of say 2 meter. So that will create a 4 plus 2, 6 meter and can inundate the entire portion of the western block that I have shown in our village level mapping. Another very important, so the tidal timing with the cyclonic landfall time becomes very important to assess the level of inundation and to predict the level of inundation. So this is our new learning from these two, comparing the two storms, observing the two storms and not being chased by them, but actually chasing them, probing deeper through our Earth observation system and coming to new scientific know-how. When we started doing the modeling with my 2-1 with one of my student Kaushik, so we observed a very important feature of the delta which was not known to us previously, because there is only one tide station at Sagar Island which was, say, if it is 4 o'clock 4 p.m. or am, this tide station is at Hupi estuary. So the another estuary is Thakuran. The Thakuran, the tide is at 1 p.m. This tide actually reached Thakuran much before Sagar. Or if it is Goshaba, the next river, Goshaba, towards the Sundarban Bangladesh border, it will be around 2 p.m. 8 p.m. to which the border runs. So you can see that if we do a storm surge modeling with an approaching cyclones, the high tide situation will vary differently at different time. So the surge may enter through a particular estuary. It may not enter to the another estuary where there is a low tide situation. So at a high tide at some estuary, maybe a low tide of some estuary to a bigger delta like this. So this is another very interesting observation that the entire deltaic part from west to east and from south to north cannot be treated as a single unit in a GIS modeling. Next, please. So we will conclude with this, and I'm sorry that because of a lot of snags, and particularly because of this slow speed of the internet connection from my home at Patuli, the entire presentation cannot be shown to you, but you can understand that we have tried to present our latest observations. Some of them are yet to be published, some of them are published uh, to you, to share with you, so that this August gathering can actually suggest uh, and can have discussion about that. But for any future storm surge modeling or cyclone study, we should be careful about the wind direction that I mentioned in my lecture, and wind direction and its change before and after the landfall. Coastal orientation vis-a-vis the surge propagation direction, taking into account the Ekman transport and due to during inundation warning issue, bathymetry of the creeks and the rivers are to be measured. The JBECO data is not sufficient to model the bathymetry here within the delta. It has to be measured as we have started measuring it with the collaboration with University of Edinburgh that and IIT Kharagpur. Uh, that where the JBECO is showing uh, 1 meter elevation, we are getting 7 meter depth, and high resolution topographic measurements are essential for this climate threatened delta, because we are a delta a delta community which are chased by cyclone and haunted by hurricanes. So if we don't have a clear-cut, high-resolution bathymetry, we will not be able to warn people who are staying in the low-lying area and actually can make the cyclone shelters at appropriate highland areas. So I think with this, I will complete my lecture in spite of all the technical snags that it can be communicated to you, so that I'm happy about that. Thank you very much.
Thank you, sir, for your detailed and articulate presentation on the fragile ecosystem of Sundarbans. Indeed, this mangrove forest ecosystem is under siege with continuously depleting biodiversity and loss of species due to both natural and man-made causes. Your presentation has given us a close look at the threats this immensely valuable tidal mangrove forest is facing both from man and from nature. Thank you, sir. I now request Professor Deboduti Mitro of the Department of Geography of our college to conduct the interactive session. Due to time constraint, only few selected questions will be placed before our speaker. Professor Deboduti Mitro, please begin the interactive session.
Okay, ma'am. Am I audible?
Yes.
Okay.
Yes, carry on.
Okay. Yes. Thank you, ma'am. And thank you, Dr. Hajra, for such an informative session. So without any further delay, let's move on to our question answer session. So, sir, can we start whenever you are ready? Sir, sir, shall I proceed? Okay, sir. Sir, shall I read out the question?
Yes, you read out.
Okay, sir. Okay, the first question comes from Dr. S.K. Das. He is asking, why Bay of Bengal is more prone to tropical cyclone in comparison to Arabian Sea?
Yeah, the answer is the Bay of Bengal is warmer, much warmer than the Arabian Sea. So more tropical cyclones are here.
Okay.
I have given it in chat. Yeah. And
okay.
Yeah, next. Can climate change make cyclones stronger?
Yes, sir.
Yes, they can make more super cyclone, because you can see that over time the number of depressions have decreased over the Bay of Bengal, but there is a 26.7% rise in the high intensity storms. That is the extremely severe cyclone. You have seen that Hudhud, Failin, then Amphan, then before that Fani, all are 260 kilometers. So you can see that already the climate change is intensifying the cyclones in the Bay of Bengal, and that is because up to the depth of, say, I was actually suggesting up to 700 meters up to the sea is now much warmer, anomalously warm. So it is supplying the fuel for intensification of the cyclone, which could have would have been destroyed if there was a less warmer sea water below the surface of the sea. Yeah, thank you.
Okay,
Next.
sir. Okay, sir. The next question is East coast of India is highly vulnerable to cyclones than West coast. What are the reasons behind it?
Because it is the Arabian Sea is facing lesser amount of cyclone, and Bay of Bengal is facing much more number of cyclones. And from the south to north, if you see from Chennai to Odisha and Bengal, every year these coasts are devastated by cyclone. So Bay of Bengal is warmer. The favorable conditions for cyclone formation is there. It is closely connected with the El Nino system and the Pacific Ocean, because there are a lot of cyclones like Komen and others, which actually between the Pacific and the Bay of Bengal, we have very thin landmass. If you think of your map, then some of the tropical cyclones can actually cross the Andaman Java, this peninsula, and can come to the Bay of Bengal and can devastate, like Failin did. So there are supply from the Chinese part, you can say that. So there is different threats from the Pacific cyclone system, which is not there in the Arabian Sea, yeah, and the West Coast. Next,
Devotati, it must be the last questions because we are running out of time. Other
yeah,
speakers are also waiting.
Okay.
already
Okay.
answered,
There are no more
and I will
questions,
answer
are
it
there?
in the chat. Yeah, so you can
Yeah.
continue with the next speaker, maybe.
Yes,
Okay.
sir. Thank you, sir,
Mm.
for your time and patience for clearing our doubts. So with this, we end our interactive session.
Thank
Now,
you.
Alo ma'am.
Okay, I'll continue. Okay. Thank you, Professor Devaduti Mitru, and a big thank you to the participants of this interactive session and the entire audience. Thank you, Dr. Shugata Hajra, for your gracious presence in our webinar. Your presentation has brought forth valuable insight into the pressing problems our precious Sundarbans is facing. Thank you, sir. Stay well. With this, we complete our technical session 1. I now invite Dr. Gargi Basu of the Department of Economics of our college to begin technical session 2. Over to you, Gargi.
Thank you, Alagi. Very good evening to all, and good morning, Dr. Scott Brown. Yeah, I think he's already with us. In this second technical session, we are glad to have Dr. Sanjeev Kumar Singh as our speaker. He is currently a scientist at Indian Institute of Remote Sensing, Government of India. He had completed PhD in mathematics from ISRO, Ahmedabad. He had research fellowship from Space Application Center, ISRO. Dr. Singh worked as project scientist at National Center for Medium Range Weather Forecasting, Ministry of Earth Sciences, Government of India from 2012 to 2017. From 2018 onwards, he is working at IIRS ISRO Dehradun. His research experience is in the fields of tropical cyclone, numerical weather prediction, model, and remote sensing data assimilation in the NWP model. His works and have been published in many national and international research journals of reputations. Now I am requesting Dr. Sanjeev Kumar Singh to deliver her speech. Sir, it's over to you. Dr. Singh.
Hello, sir. We can hear you.
Sir, please.
He here?
No, I don't think he's there.
Oh, he's here. I can see.
He's here. Yes, I can see his name, but I can't see his video or audio. To unmute.
Yeah, he's there. He's unmute. Like he's muted.
Gargi or Indrani, please get him over phone. Give him a call. Give him a call.
No, he's there. He's there.
No, he's there, but there's a problem. Said that, so we have to wait too. Yeah, make him a phone call. That will be better. It's my suggestion.
Dr. Sanjeev Kumar Singh, can you hear us? Can you respond, please? Danidi or Alodi, can you please call him?
Okay, I'm trying. I'm trying.
I think there's connectivity problem because his audio is on.
Audio is showing he's unmuted, but I mean it's green, but I can't hear anything from his end.
Yeah, maybe connectivity is poor.
I have just talked to Gargi. Can you hear me?
Yes.
Here. He has. I have talked to him. Some technical problem is there. Probably poor network connections there. So he has requested me to request Dr. Scott Brown to if he just wishes to give a presentation. So, Dr. Scott Brown, can you hear me?
Yeah, I'm here.
Yeah, actually, our second speaker, he has some problems in his computer, so he's trying to solve the problem. So he has requested me to continue. So are you ready?
Yeah. Let me share my.
Okay. So Gargi. So
yes.
Yeah. So Dr. Brown is ready. So I can introduce him.
Okay. So instead of the technical session 2, we will start technical session 3.
Yes.
And after that, we will continue with the second sessions.
Okay.
So it's over to you, Indranidhi.
Good evening, good afternoon, good morning. Join us through the incredible journey to learn more about Mother Nature with amazing speakers who are here to help us for better understanding of nature. It's a great pleasure to have Dr. Scott Brown with us today. Dr. Scott Brown, a research meteorologist at NASA Goddard Space Flight Center, is the project scientist for NASA's GPM and Tropics mission and is a member of the Science and Applications Leadership Team for NASA 2017 Decadal Survey Aerosols, Clouds, Convection, and Precipitation Study. He was previously a project scientist for the TRMM satellite and the principal investigator for the Hurricane and Severe Storm Sentinel HS3 airborne investigation. He received his PhD in atmospheric sciences from the University of Washington, Seattle. With lots of awards, numerous publications of internationally reputed journals, he is an outstanding person in real sense. We welcome you, Dr. Scott Brown.
Well, thank you for having me. Are you able to see my screen all right?
Yeah.
Are you able to see my screen all right?
Yes, yes, it's working fine.
Okay. Well, this presentation has a number of animations. So I'm hoping the network connection will allow them to play fairly smoothly for you. I think obviously it goes much better if that moves smoothly along. So this is a talk that I've given before, most recently at the Library of Congress here in Washington, D.C. It's intended generally, it's intended for a more general audience, focusing on what NASA does for what we call hurricane hunting. Um, so what is hurricane hunting? It usually refers to efforts to collect information on tropical cyclones to improve the forecast. So there's a couple different motivations for it. One is, since these storms occur primarily over the oceans, we typically have very little in the way of in situ observations within them. We have imagery from satellites, but that only tells us so much about what's going on in these storms, particularly their exact center location and their intensity. And so often, particularly in the Atlantic and increasingly some countries in the Western Pacific are starting to fly aircraft through tropical cyclones to collect this type of information. This information is not only used for monitoring the storms, but it's often used to collect data that can then be brought into numerical forecast models to improve the forecast. Sometimes this is data from dropsondes and flight level winds, as indicated in the lower image here. But increasingly, with some aircraft, it involves collecting radar data that gives you much better coverage. And that data has shown to have a pretty profound impact on the forecast. So as we move forward here, I want you to sort of imagine that you are the forecaster, and we're going to look at a couple of situations involving the same storm. This is a storm that could potentially impact millions of people and cost millions, if not billions of dollars, depending on the extent of the damage. Now, in the first case on the left, this is shortly after the storm is formed. It's got a fairly simple track. Most of the models track it to the west where it would make landfall. The S you see in these black circles indicates a tropical storm intensity, so not reaching hurricane intensity. And the forecast suggests it would move across Mexico into the southern Gulf. And from there, you might just extrapolate it to the west or the eastern coast of Mexico, and also assume that it might remain a weak tropical storm. Now, this is fairly early on in the forecast process, so it is maybe not as critical of a forecast. But then we find several days later that once it's gotten into the Gulf of Mexico, its track has changed quite a bit. It's just a little farther north in the Gulf, and now instead of going toward Mexico, it's expected to go up toward Texas. And you can see that the track suggests that maybe it slows down after landfall and then gradually turns to the east. Again, the S's in these black symbols suggest that at this point, the forecast anticipates it remaining a weak storm. But we also know that the Gulf of Mexico is anomalously warm at this point, and those types of ocean conditions are favorable for storm intensification. So we have to be on guard, particularly for what we call rapid intensification, which is a storm that intensifies by about 30 knots in 24 hours. Now, this particular case is actually from Hurricane Harvey back in 2017. And some of you may be familiar. It's a storm that actually underwent rapid intensification. Now, to be able to develop a better forecast here, we need more information about what's going on in the storm. And so typically, we send aircraft out into the storms. And there's two organizations that do this routinely or operationally. One is NOAA, the National Oceanographic and Atmospheric Administration. They'll fly aircraft like their P-3 Orion aircraft that releases dropsondes, which are small tubes with sensors to measure temperature, humidity, pressure, and winds as it falls to the surface. It has a radar that measures the horizontal precipitation structure here on the belly of the aircraft. And then in the tail, it has a spinning Doppler radar that as the aircraft flies through the storm, it's mapping out the three-dimensional structure of precipitation and winds within the storm. And this is particularly valuable data. NOAA also has a high-flying G4 aircraft that releases additional dropsondes from a higher altitude and also has a tail Doppler radar. And even though it can't get into the core of the storms, it can collect information on the precipitation structure farther out from the core. So these aircraft are typically tasked when a storm is threatening either the islands of the Caribbean or the U.S. coast. Now, the other organization that flies the aircraft is the Air Force, and they fly their C-130 aircraft, also turboprop aircraft. They primarily collect dropson data and then information from an instrument called the Step Frequency Microwave Radiometer. And the purpose behind that instrument is, you may be familiar that as the wind speed increases over water, the water tends to get choppier, waves get bigger. And so the idea with this instrument is that by measuring the roughness of the ocean surface, you can get an estimate of the surface wind speed. And so that's what this instrument is able to do. And it proves to be a very valuable way of mapping out the surface wind speed along the flight line. So this is, again, the routine observations that are collected. Now, NASA is a different organization. We're more of a research organization, but we still like to hunt storms when we can. And we do this in a few different ways. But first, the motivation for our hunting of hurricanes is that we want to better understand hurricane structures, such as precipitation and winds, formation mechanisms, and intensification mechanisms. Now, we're a space agency, so our top mission is to learn how to do this from observations from space, from satellites. And so I'll spend some time in this talk. I'll spend a lot of the time focusing on these spaceborne observations. But occasionally we also go out with aircraft to do what we call field campaigns to collect in situ and remotely sensed data sets that help us to better understand these storms. And again, this is all for the purpose of these different subjects that I mentioned above. And then I'll finish up this talk with a brief summary. Well, sorry, I just blew my one joke in this talk here. I usually say, well, to really understand how hurricanes work, you need to understand the basics. And then I would go to this. And unfortunately, that joke just failed since I moved forward. And it probably also works better with when I'm actually in front of the audience versus a phone call like this. So anyway, this would have been the joke had it worked. But these are the types of equations that scientists use to describe the science or the dynamics of hurricanes. But we're going to start at a much more basic level about the basic structures of a hurricane. And we'll focus on the northern hemisphere so that we don't have to keep changing the sense of rotation if we jump to the southern hemisphere. So your basic hurricane is best known for its eye wall. This is the region of heavy precipitation and winds in the near the eye of the storm. It's associated with very strong upward motions. The winds are rotating counterclockwise, or what we refer to as cyclonically, meaning in the same sense as the rotation of the Earth. Low-level winds are often are generally moving inward toward this area of low pressure, rise up within the eye wall, and then spread outward in the upper dense cirrus overcast. Now, in the eye wall, again, things are moving counterclockwise, but as you get to the upper troposphere, near the core itself, it might be continuing in this counterclockwise direction. But as the air flows out in the dense overcast, it changes direction and flows anticyclonically or in a clockwise direction. That is the outflow layer of the tropical cyclone. And is usually the part that you are seeing most in satellite imagery. In addition to the eye wall region, you also get these outer bands of precipitation. They don't generally present as much of a hazard in terms of strong winds, but they can also be associated with heavy rainfall and sometimes at landfall with tornadoes. So there are a couple of questions that we typically ask that are really kind of our top research questions. And those are, how do storms form and what causes rapid changes in intensity? And I'll spend a little time talking about both of these subjects. So how do hurricanes form? You need a set of basic ingredients to get storm formation. One is you need warm ocean temperatures, typically greater than about 26 degrees Celsius. And this is why hurricanes typically form down in the tropics, because the ocean temperatures get colder as you go to higher latitudes. The warm ocean really is the energy source for tropical cyclones. Without this additional energy, these storm systems would never really amount to much more than large convective storm systems. So this is really critical. You also need high humidity. That favors the development of clouds. And also, when a storm gets dry air entrained to it, that dry air tends to evaporate the cloud and can cause cooling in a way that brings colder air to the surface, which then can remove some energy available to the storm. You need weak vertical wind shear, and I'll describe this a little bit more in the next slide, but it's the change of winds with height. And ideally, for a storm to form and intensify, you want fairly weak winds in the environment. Winds that are increasing with height or changing direction with height quite strongly tend to rip these storms apart. You also want background rotation. At a basic level, this comes from the rotation of the Earth, which is why storms typically do not form along the equator. But often it's also associated with large-scale weather patterns that can provide some rotation. In the Western Pacific, this might be a big monsoonal gyre. In the Atlantic, it's often wave disturbances that come off of Africa. And then the last thing you need is a initiating convective system. This is a large thunderstorm system that helps to concentrate that rotation onto much smaller scales. And in the process of concentrating the rotation, it rapidly spins things up. So these are the necessary ingredients. They've largely been known for a good long period of time, but how they come together in all circumstances is still fairly poorly understood. We're getting better at anticipating genesis, but there are still some significant challenges there. Now, this diagram just illustrates vertical wind shear. In a case without wind shear, you would just have the low-level cyclonic circulation and the upper-level cyclonic circulation on top of each other. It would be vertically stacked, and that's favorable for development. But wind shear is when, for example, you have weak westerlies at the surface and increasing westerlies with height, so that you have what we call westerly wind shear. That basically means that this low-level vortex is moving to the east very slowly, while the upper one is moving to the east much more rapidly. So you tilt the storm over. This makes the storm much less efficient in terms of its intensification processes. And if it becomes large enough, this tilt will eventually rip the storm apart. And I can give you a fairly dramatic example here from satellite, where in this region, you're seeing the low-level center and its associated clouds. The storm center is somewhere in here. And out in this area is where you would find the upper-level center associated with the dense overcast. And again, this is very unfavorable. There have been occasions where this wind shear can initiate strong thunderstorms along the edge of the low-level circulation and spin it up for a period of time. That tends to be relatively short-lived. So the next big question is, what drives rapid intensity changes? And this refers to cases that either have very sharp drops in surface pressure and rises in surface wind speed in a short period of time. So a typical atmospheric pressure is about 1,000 millibars or hectopascals, and a very low value typically might be around 900 or so. And so in this particular case, where the storm dropped down to about 880, you can see it did so in about a 12 to 24-hour period. And coincident with that, we had the storm go from being just a tropical storm up to a strong Category 5 storm. This is on the Saffir-Simpson scale for hurricanes, Category 1 being a minimal hurricane, Category 5 being a catastrophic hurricane. And this can happen very quickly, in this case, within 24 hours. And the animation that I'm showing here is from Hurricane Wilma. The same storm is shown in these plots that, again, went through this rapid intensification. It made landfall here on the Yucatan Peninsula of Mexico and then moved northeast to hit Florida. This was during 2005, which is a record-setting year in the Atlantic for tropical cyclones. The background color shows the ocean temperatures, and what you're seeing is a loop of the geosynchronous satellite information. You can see the very large eye that forms at this point. There had been a smaller eye at the earlier time. Now, typically, when I give this presentation in front of a live audience, I will ask them to raise their hand when they think this period of rapid intensification occurs. And they'll typically say it's this period where you get this fearsome-looking large eye. But in fact, the rapid intensification occurs very early in the storm life cycle. So the storm's getting its act together here, and it's right when this, what we call a pinhole eye, forms, that we're getting this rapid intensification. The storm then underwent what we call a eye wall replacement cycle, which then led to the smaller eye being replaced by a much larger one. That typically leads to a bit of a weakening of the winds, and in this case, kept the storm at a still intense level, but not as intense as it had been earlier. And some of the key ingredients for rapid intensification also involve a lot of the same ingredients for formation. That's intense thunderstorms, very warm oceans, low wind shear, and moist air. So in observing hurricanes from space, it's really pretty amazing now the breadth of the observations that we can get from space. As you've seen, we can readily measure clouds. We've been able to do that since the late 60s, early 70s with our first satellites. Rainfall is a more difficult quantity to measure, but since the late 80s, we've had sensors up that have had capability of measuring rainfall. Sea surface temperature can be derived from a few different types of measurements. Moisture and humidity, also air temperature. Wind still proves to be one of the more challenging observations from space, but there are a few techniques for getting at least limited wind information. And then there's lightning information, which now with the latest generation of geostationary satellites in the US and in the future with European and other satellites, I think we'll be eventually moving toward global lightning observations continuously. So let's take a look at the evolution of our ability to observe clouds from space. The image on the left is from the TIRAS-3 satellite. I believe this is from the very early 70s. You can see it's a very grainy image. If you didn't know better, you wouldn't even recognize, you'd see that there's a big cloud system here, but you wouldn't necessarily be able to tell that is even a hurricane. Contrast that to what we're getting from the latest generation of GOES satellites. That's the Geostationary Operational Environmental Satellite here in the US. It has very rapid refreshes and observations about every 5 minutes over the whole US. And we can even focus on an individual storm and get observations about every 30 seconds to every minute. We have about 3 times the number of channels that we used to have, and also about twice the horizontal resolution. So we can see far more detail spatially, and because of the rapid updates, we can really track the evolution of individual clouds. This is from Hurricane Harvey during 2017, that forecaster example that I showed earlier. And this is during the period of rapid intensification. If you watch carefully, you can see the thunderstorm activity occurring here near the center of the storm. And that's partly what led to the rapid intensification. And you can certainly see the counterclockwise rotation in the core. And if you watch carefully at these, looking at these thinner high clouds, you can see how they are actually moving around in a clockwise fashion. And that's that upper level outflow at the top of the storm. So this infrared and visible imagery that we've had now going back to the early 70s is extremely useful. It allows us to track storms that prior to satellites we would often not have detected at all, or maybe not until the storms made landfall. But in many cases, they still present challenges because you're only seeing the tops of the storms. And this is particularly difficult in an unorganized storm where the center is very hard to see. Now, in this particular example, your eye might be drawn to what you think is the center somewhere in this area. This looks like it's potentially a shadow associated with this deep thunderstorm activity. There are other examples where you would have no idea where the center is really. And so one of the ways in which we are able to get better center locations from satellite is with satellites that measure microwave energy. So the clouds and precipitation emit the liquid in the clouds and rainfall emit microwave energy. The ice at the top of the storm scatters it, and those signals we can measure from new satellites, such as on the TRIM and GPM satellites, as well as several others. For example, the Megatropiques satellite, which is a French ISRO satellite taking measurements in the tropics. Hold on, I've got something on my, something popped up on my computer. I'm having some difficulty clearing it. Okay, hopefully that won't cause problems. Let me move to the next slide. Now it doesn't want to advance here. Okay, here we go. So this is what the data from microwave imagery looks like. So whereas the clouds show you the broad area where the system well, again, is providing clouds, the microwave imagery in essence gives you an X-ray looking into the storm. So now you can see very clearly where the rainfall is occurring. Here is the eye wall. So the center would be right in the middle of this. We see the heaviest precipitation here on the western side of the eye wall. And then we have these spiral rain bands that extend to larger distances away from the center. And you can see that the area of precipitation is nowhere near as expansive as the cloud shield. And so this kind of shows why if you're trying to estimate rainfall just from the geosynchronous data, you would generally overestimate the rainfall, at least its coverage, and typically it underestimates the intensity. So this gives us a much better way to track the structure of the storm. And that structure offers telltale clues about what's going on. To what extent is it being impacted by wind shear? Is there the possibility of a secondary eye wall forming that might end an intensification period, and things of that nature? This is an animation showing data from the GPM satellite. GPM stands for Global Precipitation Measurement. It has a microwave imager, similar to what I showed you before, that gives us that two-dimensional view of precipitation at the surface. So in this case, you can see the center of the storm here, the eye walls in this region, and there's actually a secondary eye wall in this other area. This data that you see kind of going across, back and forth across the domain is from a precipitation radar. The warmer colors indicate rainfall, and the blue colors indicate basically snowfall at the top of the storm, where the atmospheric temperature has fallen below the freezing level. This is showing now the most intense areas of precipitation and then going back to some of the lighter ones. So you can see in this region, here's the eye wall, a secondary band, and frankly, you can really look at these features like on the sides of the storm, and there's just amazing detail available within this radar data. So we first got this type of radar data with the TRIM satellite that launched in 1997 and ended in 2015. GPM launched in 2014, and if instruments in the spacecraft stay healthy, we could potentially continue to get data into the 2030s, but that all depends on whether or not the spacecraft and instruments remain healthy. Now, GPM is the most accurately calibrated microwave sensor in space, but it's not the only one. There are several other operational and research satellites out there, and we can use the very accurate information of GPM to calibrate the data that we get from these other satellites, and then use those calibrated data sets to generate rainfall at more than just the overpass time. So what we do is we take all the different microwave data, we apply morphing to extend that data forward and back in time a little bit, and then we fill remaining gaps with geosynchronous data. And that allows us to create these types of visualizations of rainfall that may show several tropical cyclones, but you're able to then see the evolution of these tropical cyclones in a way that we really hadn't been able to do prior to the TRIM and GPM missions. This data is also valuable for tracking total accumulation of precipitation as shown in this plot. This is from Hurricane Harvey. Here it is about to make landfall. I apologize for the graininess of the image. The color scale goes up to about a little over 1,000 millimeters of precipitation. And this is a case that led to very bad flooding in the Houston area. You can see that at the time Harvey made landfall, it sort of meandered in that area, gradually moved offshore, and it was around the Houston area for about 5 days. With this animation, we tracked it as having on the order of about 700 to 800 millimeters of rainfall, or 30 inches. In the end, Harvey produced about 5 feet of rainfall in the Houston area. It was a very devastating flood event. Now, another way that we are able to observe storms, or a critical piece of the information for storms, is through measuring sea surface temperature. We've been able to do this from visible and infrared data, but you couldn't see through clouds, so you always wondered what's going on underneath the storms. And then with the TRIM satellite with microwave imagery at a particular frequency, we were actually able to see the ocean temperatures even beneath the clouds, which allowed us to start seeing the interaction of storms with the ocean. Now, this animation is from the 2005 hurricane season. The warmer colors indicate where ocean temperatures are favorable for hurricane development. The blue colors are where it's generally too cold for development. And this again was a very active season. And we'll kind of point out different things as we go along here. So one thing you may notice for some of these storms is that as they move along, the orange colors change to blue. That is due to the fact that the strong winds within these storms mix up the very thin layer of warm water at the top of the ocean, at the surface, and pull up deeper, colder water. And it takes several days then for that colder water to return to normal. That can have significant impacts on subsequent storms that come to that area. Now, I want to point your eye to this feature here that kind of looks a bit innocuous. You wouldn't know that much is going on until it got to just off the east coast of Florida, and it became Hurricane Katrina, underwent rapid intensification of the Gulf. Its strong winds, as you can see, cooled the ocean. And Katrina is the storm that was just so devastating to the New Orleans area, led to about 2,000 to 3,000 deaths in New Orleans or that area back in 2005. So being able to measure these ocean temperatures from space has just been absolutely critical for understanding when and where these storms might form, and whether or not the conditions are whether there's the adequate energy source for rapid intensification of storms. I thought I would point out this anomaly chart. So, we've had a long record of ocean temperatures that forms our basic estimate of the climatology. And typically, a hurricane scientist is going to look at the departure from the climatology or the anomaly. And what we typically see in the Atlantic these days and around much of the globe is that during hurricane seasons, temperatures tend to be well above normal, anywhere from 1 to 2 or 3 degrees above normal. So that means that we're seeing much more favorable conditions for tropical cyclones. And in this Harvey case, as it made its way into the Western Gulf, you can see these very warm temperatures that led to the rapid intensification. Now, ideally, you would only see these very warm anomalies once every few years, but we are now at a state after many years of significant global warming to where this has become the new normal, which is part of the reason why people fear that we're going to see an increase in storm activity, and in particular storm intensity in the years ahead. And there have been numerous studies that have argued that cases like Hurricane Harvey, Dorian from last year that destroyed the Bahamas, and many other cases are a byproduct of global warming. Again, another ingredient is humidity, and microwave sensors are really key to tracking humidity in the atmosphere. So the microwave sensors are able to measure the total water vapor in the column, but most of that is coming from near the surface where the air is warmer. And so this usually is telling us where low-level conditions are very moist. Now in the Atlantic, most storms form with these waves that come off of Africa, and you can get the sense of the counterclockwise rotation in this disturbance. But this particular one had dry air pulled into the center, which may have, to some extent, inhibited development. Now, if you look over in the Western Atlantic and the Gulf region, you can see it's very moist. And watch this particular feature here where you can see the rotation, and it starts down here in the Caribbean and moves up into the Gulf. That is where Hurricane Harvey formed. So you can see very moist conditions and therefore very favorable conditions for development. When you get these broad intrusions of dry air, the blue and green colors, into the tropics, that generally tends to prevent or inhibit general formation and intensification. Now, the last topic we'll touch upon here is the winds. And here I'm showing a computer simulation of winds from the 2012 season. The reason I'm showing computer generated winds is because our ability to measure winds in the atmosphere is quite poor. We have some satellites that can measure surface winds over the oceans with instruments called scatterometers. They tend to have some problems in heavy rain areas, so not ideal for a hurricane, but they do give you a good sense of the rotation and some of the winds within the storm. With the geosynchronous data where you can track clouds and water vapor in these disturbances and get estimates of winds within them. But sometimes they're only at upper levels, sometimes at lower levels. So computers really give us our best representation of what's happening in the storm. And this is, if you may have heard of it, Superstorm Sandy that came up the east coast of the US and slammed the mid-Atlantic area late in 2012. It was just a devastating storm for the New York area. These computer simulations are certainly increasing in sophistication and skill. This particular simulation did a great job at representing the structure of Sandy, but I wouldn't say it's typical. In fact, when I look at reanalysis data from whether it's from NASA or other organizations, you'll still find that the representation of tropical cyclones in those global analyses tends to be quite poor. Part of that's due to the resolution of the model. In fact, that's probably the biggest problem with it. This particular simulation was done at a very high resolution, which allowed it to do a better job. But again, this remains one of our bigger challenges. Now, most satellites have been quite large. I believe this is the GPM satellite. And you can see this big instrument here. It's the size of a person, and the satellite as a whole is the size of maybe a small school bus. This is what we've had to launch in order to get these amazing observations. But the trend now is to try to move things toward much smaller satellites. And I'm showing an example here of a satellite called RainCube. You can see it's much smaller. It's about the size of a small desktop computer. Now, it's not nearly as capable as this bigger satellite, but it does show potential for the types of observations it's able to collect. The advantage of these smaller satellites is they're a lot less expensive, and you might be able to launch a much larger number of them to form constellations of satellites. And so this is one area where NASA and other organizations are making investments to see if we need to change the way that we do our global constellation of Earth-observing satellites. So I'll show you an example from that RainCube satellite and from another one called Tempest. This one is a microwave radiometer, so it's mapping out the horizontal structure of precipitation, and it can do that at a few different levels using different frequencies. And then again, RainCube is a radar, and in this case, it just gives you a vertical curtain of data. And here's an example from one of the storms where the two satellites flying close together took observations. And I don't recall I believe this might be Typhoon Trami, but I don't remember for certain. But this data that you see, where you see more of the vertical orientation, is from the radar, and it shows you the vertical structure of the precipitation. And then these four layers that give the horizontal structure are from the microwave imager. And because they're measuring at different frequencies, it can give you 4 different levels, but it really gives you a good sense of the horizontal structure of the storm at these different levels, coupled with the radar. And this really could be the wave of the future of satellite observations. Now, one of the first major missions, those were both demonstration missions. One of the first big satellite missions that we have coming up using these types of microwave radiometer measurements is called TROPICS, which stands for Time Resolved Observations of Precipitation Structure and Storm Intensity with a Constellation of Satellites. Very long name, but it made for a great acronym. But our main goal with this constellation is to get rapid update observations with a constellation of 6 different satellites that can profile temperature, humidity, and we'll be able to map out precipitation structure. We'll have 2 satellites, each in 3 orbital planes, so that we get this sort of coverage over the tropics over about a 24-hour period. Here's an image of what the satellite, this is the newer version of the satellite. This was an older version. It's about the size of a large loaf of bread, and this is the instrument. This is the satellite payload. So you can see it's quite an advancement over what's been done in the past. We expect that this satellite will launch in early 2022 and hopefully go for up to about 2 years, 1 at a minimum, but hopefully about 2 years of observations. There are a variety of applications that the satellite data offer, including numerical weather prediction, direct use by forecasters and emergency responders, flood and landslide monitoring. The power industry can use this to anticipate where power will get knocked out and where they need to put resources for bringing power back. Because standing water from rainfall can lead to mosquito-borne diseases, the rainfall information is used for disease monitoring. And then the insurance industry is using the data nowadays as a way to assess risk so that they can insure the insurers. It's called reinsurance, and they become one of our biggest users. So now let's move on to airborne observations. This is a video from the NOAA aircraft, but I like to show this because, one, it gives you a sense of how rocky it is to fly through one of these storms. It's very bumpy. But once you get into the center of the storm, it offers an amazing view to the few people who in their lifetime have been able to do this. I've been fortunate to be able to do this a few times in storms. Once in a storm much like this that had a clear eye where you could see what we often call the Colosseum of the storm. So now as the plane tilts up, you can see the inner edge of the eye wall and the blue sky aloft. And it's just a phenomenal view within the storm. Now, NASA has had a number of field campaigns over the years. I've been involved in many of these where we fly different aircraft into the storm. One is our DC-8 aircraft that has people on board manning a lot of different instruments. It flies at a higher altitude near the top of the storm. We've had an ER-2 aircraft that flies above the storms. And starting in 2010, we used, for the first time, a large unmanned aircraft called the Global Hawk that can fly for up to 24 hours. And this is one storm, Hurricane Carl, back in 2010, where we had the Global Hawk coming from California out to the Gulf. We had NASA aircraft, NOAA aircraft, and the Air Force aircraft all converging on the storm at the same time, collecting observations. So we collected a wealth of information here. Each of these crosses represents lightning, and the colors represent the satellite data showing the cloud tops. You can see most of the aircraft have left. A second Air Force aircraft had come in to take observations. The Global Hawk continues to measure, and eventually that Air Force aircraft will leave and the Global Hawk will continue on its own. It stayed over the storm for about 14 to 15 hours of continuous flight. And that was even coming from all the way over in California. So move on, if I get this forward. This shows an example of some of the data collected from the Global Hawk. This is from a radar called the High Altitude Wind and Airborne Profiler. It scans in a cone to measure precipitation in the form of radar reflectivity, as well as Doppler velocities. And while it doesn't look all that exciting when you see the raw data, it's hard to make sense of it. You get the sense of deeper structures here and some shallower precipitation. But after we've scanned the storm through numerous passes of the storm, you can process that data to map out the precipitation and winds in the storm. So the colors here are showing the precipitation intensity, and the arrows are showing you the derived winds within the storm. And while I'm only showing the surface winds here, you have these winds through the depth of the storm. So it gives us a lot of insight into the dynamics of the storm, and the data can be used in forecast models to try to better initialize those forecast models. Now, starting in 2012 to 2014, I led a campaign called the Hurricane and Severe Storm Sentinel that focused on the global hawk. We planned on using two of them to do one focus on the environment and one focus on the inner core processes. Unfortunately, one of the aircraft that we used was the very first global hawk ever built, and it was really too old to really operate successfully. So we primarily just used the one aircraft. So we flew it from our NASA base in Wallops. We did 670 total flight hours, 21 flights over 9 named storms during the 3 years of the campaign. It was based out of Virginia, which gave us ready access. That's me there, and this is my program manager showing you our operations center. So we would have computers there that would allow us to monitor the path of the aircraft, as shown by the blue line. The red line was our original track. Here's one of the instruments, our cloud physics LiDAR, that was meant to measure clouds and Saharan dust over the Atlantic. You'll see in a moment the dropson systems. So these are the tubes that get released to measure temperature and humidity and winds as they fall to the surface. And you'll see in a moment it gets released from this tube at the back of the plane. And again, back in the control center, that's our payload manager working with the scientists who are monitoring the storm. We were also communicating with the pilots. There's me again and my advisor, Bob Howes, who you may have heard of. We would make adjustments during flight to adjust for the fact that the storm was moving, and the pilots would make adjustment to the course of the aircraft. And as I mentioned, we were trying to look at the effects of Saharan dust on the formation and development of these storms. And this is an animation showing data from the cloud physics LiDAR and the dropsons. Unfortunately, the Saharan dust doesn't show up very well in this animation, and I've always meant to get this redone, but never did. So you're seeing the upper part of the clouds and the humidity information that we collected from the dropsons. This is a nighttime view of Hurricane Edward from the aircraft, which we use then to assess how tall the storms are and whether there are any potential hazards for the aircraft. This is me at one of our science team meetings. We hold these science team meetings every year after the deployments to discuss what we did right, what we need to do better for the next year, preliminary science results, and it also fostered collaborations so that we can make sure that we are getting the most science for the time that we were putting into this. And we could also observe some of the data in real time during the course of the flight. This front room is where the pilots operated. They operated by computer. So while the plane is uninhabited, the pilots are always in control and can communicate with it and change its course as needed using just the click of a mouse button, as you can see illustrated there. So let me move on from this. This is an example of data collected in Hurricane Edward showing relative humidity from an infrared sounder on the aircraft, as well as the dropson data, which included humidity and wind information. And the nice thing about the Global Hawk being able to fly for 24 hours is that we could map out what was going on very large scales, as well as cross the storm multiple times to map out the wind field in the inner core structures. And there's no other aircraft that can allow you to do that. In a moment here, it'll zoom in to focus on the environmental moisture structure that was captured by the aircraft. So what have we learned from aircraft over the years? Well, we were able to measure the strength and distribution of intense updrafts within the eye wall in a way that just isn't possible by any other mechanism. I point to this example from Hurricane Emily in 2005. This thunderstorm was so intense that when the pilot flew over it, it almost stalled the aircraft and it would have caused a crash. And when we look back at the reflectivities from the radar, it's very much like had the signatures of a hailstorm, something that is exceedingly rare within a tropical cyclone. So it was a rather rare find. We've also got information on proposed mechanisms for storm formation and intensification, better characterization of storm structures, particularly precipitation structure. We've made efforts at trying to look at the impact of the Saharan air layer on storms, although not always with a lot of success. And we've evaluated the impact of these airborne data sets on storm track and intensity forecasts. In fact, after the HS3 campaign using the Global Hawk, the NOAA used the aircraft for 2 or 3 years to try to operationalize it and in real time bring the data sets into their forecast models with some success. So just in summary here, NASA uses the vantage point of space to get a wide range of data sets that tell us about what's going on with the Earth. And a lot of these are very relevant to the tropical cycle. Now I've focused on the Atlantic here, but obviously these satellite data are available globally for forecasters all over the world. The latest trend, though, because these large satellites are so expensive and it's hard to do them continuously, we are looking at a paradigm shift of, at the very least, not replacing the larger satellites, but supplementing them with small satellites that can be relatively inexpensive, put up very quickly, and provide some unique observations. And then finally, the airborne data sets are extremely valuable for satellite validation, testing new sensors, but also for improving the understanding of storms. So that's all I have, and I'd be glad to take time for questions if there is time.
Thank you, Dr. Scott Brown, for your brilliant presentation. It is so informative, and you have enlightened us about the different aspects of cyclone tracking and monitoring methods, which are, of course, very important components in forecasting system. Now, we have got some ideas about how do cyclones form, what drives rapid intensity changes. And I find very interesting information from your presentation, especially about monitoring storms with satellite, radars in space, giving 3D views and seeing rains from space, especially the applications of microwaves and airborne monitoring, tracking, and of course the infrared sounder and drop sounds, and so on. So many new things we have come to know. So I can see some questions are there in our chat box and questions from our participants. So I'll request Dr. Sudeshna Shahu of the Department of Chemistry to join me and to conduct the interactive session. Sudeshna?
Yes, I'm here. Thank you, Indranidhi. First, I would like to thank Dr. Scott Brown for his lucid and vivid lecture on the tropical cyclones and its genesis. And definitely, he enlightened us regarding the NASA's hurricane hunting operations and how the technical advancement they have developed to track the cyclones. So there, I found few questions raised and asked by our participants. And the first one I'm going to ask Professor Brown. The question raised by Ms. Shikha Singh, she asked, why is the southern hemisphere the occurrence of tropical cyclone is less than the northern hemisphere? Can you hear me, Dr. Brown?
Can.
Audible?
And to tell you the truth, I'm not sure if I have the best answer. I would say, most of the activity tends to be in the southern Indian Ocean and around Australia. And it really is a function of the ocean temperatures, and many parts of the southern oceans just don't have the same degree of warming that we see in the northern hemisphere. But I'm not sure I have the best answer for why that would be the case.
Okay, all right. So the next question asked by Dr. S.K. Das. So he asked, is it possible to capture all data to predict the path, strength, and timing of hurricane by the hurricane hunter?
Well, these data sets certainly have helped. There's been a lot of efforts at improving what we call data assimilation into the model. The aircraft data sometimes proves challenging to use because the models aren't always capable of bringing in the high resolution data available from aircraft, or the model dynamics. If the observations are sharply in contrast to what the model thinks the atmospheric state is, the model will reject the data. So it's really, global models present a challenge in trying to assimilate some of these data sets because the data often gets rejected. We are seeing now high resolution regional models that are more capable of resolving the structure of these storms, and therefore are more capable of accommodating the types of observations being collected by aircraft. And one of the data sets that has probably been best used within the models is the airborne radar data sets from the NOAA aircraft. Dr. Fuxing Zhang, before he passed away recently, had developed techniques to assimilate in real time data being downloaded from the aircraft, and they did find significant improvements in the forecast. I don't know whether it was ever demonstrated if it improved rapid intensity forecasts, but certainly in general, it led to improvements in forecasting. I think one of the biggest advancements that we've seen just recently in the area of satellite data assimilation is the ability to assimilate microwave data in all skies. Previously, only clear sky observations were assimilated, so all the information within the cloud systems was rejected. But in recent years, we've seen techniques develop to assimilate information even within the storms themselves, and that is leading to some significant improvements in forecasts. So I think we're really at a stage now where the capabilities to bring this data into the models has increased. And as the models continue to improve, I think we will see forecasts also improving.
Okay, very nice explanation, sir. So the next question asked by Dr. Debadute Mitra, she asked, what's the difference between a hurricane and typhoon?
It's really only a difference in name. So the general name would be tropical cyclone. And in the Atlantic and East Pacific basins, the U.S. is responsible for forecasts in the Atlantic, Eastern, and Central Pacific. And so in those basins, we call them hurricanes. And the origin of the name, I've read different things. I think it relates, it's a name that came from the Caribbean, I believe, or from Mexico. Whereas most other parts of the world refer to, in the Western Pacific, they're typhoons. Other places like we'll call them cyclones. And so it's just different forecasting organizations have ultimately called them by different names, but fundamentally they're the same thing.
Okay, thank you, sir. The next question I can see is from Dr. Sharmi Bhattacharya, and she asked, is the GPM useful for calibration only in post-hurricane analysis, or can it help with predicting the path of a hurricane before it strikes?
Well, the calibration aspect of GPM is in the sense of calibrating data from other satellites, because we've got a number of satellites out there that measure the microwave energy, but they do so with different frequencies, different resolutions, and you can't just throw them together. It'd be like mixing apples and oranges. So you need a way to kind of equalize them. And we do that through comparing them individually to GPM. And then once that calibration is done, we know that the rainfall rates that we're deriving have been done in a consistent way. And so that's really where GPM is used for calibration. But the prediction aspect of it, again, comes from the ability to do the all sky assimilation that we're seeing now, tracking the storm position, observing the behavior of the storm by looking at how things are changing within the microwave data.
Right.
So that's sort of how it improves forecasting at this point.
Okay, thank you. And I have a personal question regarding this part. So, as you said that the microwave sensors are the key for this GPM data. And you also told us about the IR sound. So, is it same as the IR imaging? Like, like we have used some IR camera and IR, infrared light for imaging part. Is that a similar thing like the IR sound? Can you just little bit explain on this IR sound? It's my personal query.
Yeah, no, so the infrared sensors are basically measuring the effective temperature of the cloud tops. So the higher, because temperature decreases with height, the higher the cloud, the colder the cloud top. But you're really only seeing the very tops of the clouds. The microwave data is giving you an estimate of, for lack of a better term, the total water within the column. And because these clouds tend to be fairly vertically oriented, you're effectively seeing what's in the vertical column associated with the precipitation. And that often directly relates to the surface that's falling, or the precipitation that's falling at the surface. Of course, the advantage of the radar that we're collecting, both on TRIM, CloudSat, and GPM, is that you're not just seeing the column quantity, but you're actually measuring the column layer by layer, so you're getting the full three-dimensional structure.
Okay. Okay. Thank you, sir. I think the last question I can take from Dr. Alu Guho, Department of Geography from our college. She asked, does the warm Gulf Stream ocean current play any role in the formation of cyclones in mid-Atlantic?
In the mid-Atlantic.
In mid-Atlantic.
Yeah, the Gulf Stream, it's, certainly where it goes up along the coast, it will offer an energy source for storms that are moving through that area. And so often when we see a storm coming up, we'll see some intensification. And for example, this case Gert that just went by in the image, given that that warm current extends offshore, any storm that is moving over that warm current has the potential to get additional energy from the Gulf Stream. Once you move away from the Gulf Stream and you're further out, its impact obviously will be less.
Okay. Okay. Thank you, Professor Brown, for your clear explanation and clarifications, and also spend time with us. So I would like to ask Professor Indrani Dash. Over to you, Indrani. Can you please give vote of thanks for us to him? Yeah. Yes.
Thank you, Sudeshna, and thank you, Dr. Scott Brown, for giving us opportunity to experience wonderful moments and also for enriching us about the amazing nature and world of science. We'll always cherish these great moments with you. Thank you, sir, so much.
Thank you, sir, for your time.
And with this, I announce end of this session, and I am requesting Gargi to conduct the next session. Dr. Sanjeev Kumar Singh is available. I can
Hello.
see. Yeah.
Welcome you all this in this technical session too. Because of some technical issues, we have to shift this technical session at the end of the program. In this session, we are glad to have Dr. Sanjeev Kumar Singh with us. Dr. Singh is currently a scientist at Indian Institute of Remote Sensing, ISRO. He had completed his PhD in mathematics from ISRO. He had research fellowships from Space Applications Center, ISRO. He worked as project scientist at National Center for Medium Range Weather Forecasting, Ministry of Earth Sciences, Government of India from 2012 to 2017. From 2018 onwards, he is working at IIRS ISRO, Dehradun. His research experience is in the fields of tropical cyclone, numerical weather prediction model, and remote sensing data assimilation in the NWP model. His works have been published in many national and international research journals of reputations. Now I'm requesting Dr. Singh to deliver his lecture. It's over to you, sir. Sir, please.
Thank you, Dr. Gargi.
Thank you, sir.
So, first, can you hear me?
Yes, we can hear you.
So first of all, I would like to thank the organizer for inviting me to give the talk on such interesting topic. And as you know, over the India, there are two periods of cyclone formation. Monsoon season and another one is the post-monsoon season. Start from October to December. So every year, on an average, 4 to 5 cyclones form over Bay of Bengal region. Bay of Bengal and Arabian Sea in both. I am talking about the North Indian Ocean. So 4 to 5 cyclones form on an average every year and that hit the Indian mainland. Because our Indian coastline is so long, it is about 7,500 kilometers long, and the density of the population near the coastline is very high. So it becomes very essential to give or to predict the tropical cyclone very accurately. That is the challenging task. So after super cyclone, when super cyclone Amphan formed, people are more aware about the tropical cyclone. They are more curious. What is the tropical cyclone? How it behave? How it follow the path? And how make a damages? So how by giving the accurate forecast, we cannot remove the risk, but we can reduce the risk as much as possible. So if you look at the statistics last 23 years, we have 4 super cyclones over North Indian Ocean. Out of 4, 2 super cyclones form in Arabian Sea and another 2 form in Bay of Bengal. The Arabian Sea super cyclone, one super cyclone formed in last year 2009, that is Cat, that is dissipated in Arabian Sea itself. Another in 2007, that is the Gonu super cyclone, which made the landfall over the Oman coast. But another 2 which formed in Bay of Bengal that made the landfall over Indian region. One is the super cyclone that is called Odisha super cyclone, which formed in 1999 and hit the Odisha coast, and another was the Amphan. So my today topic is on application of satellite observations and numerical weather prediction model for tropical cyclone. So we will talk about the how satellite observations we are using to monitor and tracking of the tropical cyclone and numerical weather prediction model for tropical cyclone. What is numerical weather? Numerical weather prediction model is set of some differential equation that describe the state of the atmosphere. It based on the conservation of motion, continuity equation, conservation of energy, conservation of mass, ideal gas law. It is based on that equations, and that equations converted into the computer, and then that is called the numerical weather prediction model, and that equation used to solve the atmosphere weather. So before going to the application part, I'll discuss some about the tropical cyclone, because already previous 2 speaker has deeply discussed about the tropical cyclone. So it will be easy for me to make you understand what is the tropical cyclone and how it forms. So mainly tropical cyclone is warm core low pressure system that is synoptic scale phenomena. Synoptic scale means it can be called as large scale also. It is about 1,000 kilometer or more. And it is highly organized deep convective cloud, and it forms over the warm ocean. It has some property. Near the surface, the cyclonic wind rotate anti-clockwise, and upper level, because the tropical cyclone is not surface phenomena, it can extend up to 10 to 12 kilometer in troposphere. So upper level wind is clockwise. So near the surface, wind is convergent, and upper level it divergent. And opposite phenomena in southern hemisphere. All of you know that these tropical cyclones are associated with high wind speed, heavy rainfall, and storm surge. So shall we call all anti-clockwise rotating wind is cyclone? No. Answer is no. We cannot call as a cyclone until unless the wind speed is not greater than a certain threshold decided by the Indian Meteorological Agency. So these are some criteria set by the IMD. If any cyclonic disturbance has happened over the ocean, they have set up based on the wind speed and pressure drop, that like if it is less than 17 knots, if you convert this knot into kilometer, it will come around 31 kilometer per hour. If wind speed is less than 31 kilometer per hour, then it is called low pressure. If wind speed is in between 31 to 49 kilometer per hour, that is called depression. Likewise, if wind speed is 50 to 61, it is called deep depression. And if wind speed reached up to 62 kilometer per hour, then only we call the cyclonic storm. And thereafter, if further that intensity increase, then we call the severe cyclonic storm, very severe cyclonic storm, and then categorize into the extremely severe cyclonic storm. When the wind speed is greater than equal to 222 kilometer, then we call the super cyclone. So these are the 6 major formation basins where tropical cyclone forms. And one thing I forgot, that in previous lecture somebody has asked what is the difference between cyclone and hurricane. Actually, cyclone and hurricane property are same, but these are the regional specific name. Like if any cyclone form over Indian Ocean, we used to call a cyclone. If that cyclone form in Atlantic Ocean, that is called hurricane. If form in Western Pacific and South China Sea, we call typhoon. If it is form in Australian basin, that is called valleys. So it is the region based name, but property are same. So these are the major 6 formation basins where tropical cyclone form. Indian Ocean has divided into 2 categories. North Indian Ocean, north of the equator, that is called the North Indian Ocean. And south of the equator called the South Indian Ocean. Western North Pacific Ocean, Southwestern Pacific Ocean, here North Atlantic Ocean, and Eastern North Pacific Ocean. So these are the 6 major basins. So if you look at the last 23 years, starting from 1997 to 2009, what is the statistics? What is the tropical cyclone formation statistics? This picture we have plotted based on the IMD observation. If you look at from to 2009, on an average, every year 4 to 5 cyclone forms. But in last 2 years, if you look at this graph, last 2 years, the tropical cyclone formation rate has increased. In 2019, highest number of tropical cyclone formed so far in last 23 years. If you categorize this tropical cyclone in basin-wise, Bay of Bengal and Arabian Sea, you can see In this plot, the number of tropical cyclone more in the Bay of Bengal region as compared to the Arabian Sea. Here, blue line shows the number of cyclone in Bay of Bengal, and green line shows the number of cyclone in the Arabian Sea. So out of 23 years, you can see the red highlighted arrow shows in this year there is no cyclone in Arabian Sea. Only Bay of Bengal has contributed the cyclone. And why more number of Bay of Bengal cyclone? The reason is because our Bay of Bengal sea surface temperature is Bay of Bengal ocean is more warmer. Sea surface temperature is more. Why it is more? Because Bay of Bengal receive more rainfall, and more number of river drain into the Bay of Bengal also. So receiving more rainfall and more fresh water, what is happening? Fresh water flux is more. Due to fresh water flux, SST gets higher. And another reason is, though in Pacific Ocean so many tropical cyclone forms, and that remnant also move due to easterly wind, moves in the Bay of Bengal region and again intensify. But the Arabian Sea, the tropical cyclone formation, either it forms in situ in the Arabian Sea, or it steered from the Bay of Bengal. But whatever cyclone form in Bay of Bengal, after hitting the land, it gets dissipated. So very less number of tropical cyclone intensify in Arabian Sea by crossing the mainland. So if you talk about the percentage contribution from 1997 to 2009, around 35% tropical cyclone formed in Arabian Sea and 65% tropical Bay of Bengal. But this statistics has slightly changed in last 10 years. If you look at this graph, that Arabian Sea contribution has increased by 5%. So the ratio is 60-40. So 60% has cyclone form in Bay of Bengal and 40% in Arabian Sea. So it has been noted that equal number of depression and deep depression also form in North Indian Ocean, even more also. Here 4 to 5 cyclone form, but if you look at this graph, on an average it will come 5 to 6. So every year 5 to 6 deep depression and depression forms, but it has not converted into tropical cyclone speed because of lacking some favorable condition. So due to this, they not form. This is the trend analysis of 23 years and 10 years. If you look at from 1997 to 2009, the formation of the tropical cyclone is slightly increased. But in 10 years, if you see, the rate of increase is more as compared to the 23 years. And similar trend you can find in this Bay of Bengal and Arabian Sea. So if you see category wise, like tropical cyclone, severe cyclone, what is the statistics? So cyclonic storm in last 10 years, it is showing increasing trend, slightly increasing trend. Severe cyclonic storm, it is almost constant, even slightly negative. But the very severe cyclonic storm and extremely severe cyclonic storm rate has increased. It means whatever cyclone form in the North Indian Ocean, they gain the intensity. More intense tropical cyclone is forming over the ocean. And this plot shows the super cyclone in last 10 years. Last 10 years, this plot we have not included 2020 super cyclone Amphan. Last year that one super cyclone has formed in Arabian Sea. But 3 years, total 4 cyclones has formed, including this year super cyclone. So condition favorable for tropical cyclone formation, it is already discussed by the previous speaker. So we are not going to discuss this one. One thing I want to highlight in this condition, sufficient core-release force. This is most important parameter for the tropical cyclone, because sufficient core-release force is the responsible for rotating the cyclonic wind in anti-clockwise direction. So core-release force is minimum near the equator and maximum near the pole. So it is increasing with increasing latitude. Near the equator, core-release force is 0 and maximum is at the pole. So that's why the tropical cyclone is not formed plus minus 5 degree of the equator. So beyond the plus minus 5 degree, there is enough core-release force to circulate the cyclonic wind. So this is the mechanism of the tropical cyclone formation. When the ocean is warm, what is happening? When the ocean is warm, moist air goes up. Moist air goes up. And when it came into contact in the cold air, it condenses and form the cloud. That is the deep convective cloud. So if this process is continued, low pressure column has been developed. That around the low pressure column, the wind starts circulating. If this low pressure continuously is decreasing, wind speed is continuously increased. So it is directly inversely proportional to the pressure drop. Pressure drop decrease, wind speed is increased. What is the energy potential? We know that the main energy potential is warm water and humid air. When warm water is warm, moisture goes up, it condenses at higher altitude due to low temperature. It condenses and water vapor convert into water droplet or rain. And this transition release the latent heat. And the latent heat is the main source of energy. Out of total, only 3% the released heat is converted into kinetic energy that is used to maintain the tropical cyclone wind. So this is the typical vertical structure of the tropical cyclone. You can see in the center, there is calm weather. There is no cloud, no wind. It is roughly around 10 to 15 kilometers in diameter. If you go further from the center, in both the directions, there is a dense, deep convective cloud. Like in this picture, you can see the dense, deep convective cloud at a height of 10 to 12 kilometers. This is called the eye wall. Eye wall, the region where the maximum wind lies. And if any cyclone hit the coast, this eye wall region is the most important region where damage is more. And if you go further from eye wall, there is a small narrow band. That narrow band is also called the rain band, that is responsible for the rain, and it can extend in horizontal scale about 1000 kilometers. If any cyclone form over the ocean, they will get the name. Why name is required? Because it is easy to communicate with the common people. If forecasters are giving any information, people can easily understand from this information is for what tropical cyclone. And another reason is what is happening sometimes simultaneously two cyclones forms over Bay of Bengal and Arabian Sea. If forecasters are giving the information, common people, if name is not there, common people will mislead. This information is for what cyclone. So it will be easy if cyclone has some name. In World War II, first time it started the naming of the giving the name of the tropical cyclone, and later on it is adopted by all other region also. And this name they have chosen like based on the male and female name. But over the North Indian region, the name is not based on the male and female. The majority of the name is based on the flower or animal or bird, tree or foods. So it is first time in North Indian Ocean naming started since October 2004. Who give the name? That is the question. So over the Indian Ocean, there is 13 Asian neighborhood country and their meteorological agency that participating to give the name. Each year, each country gives the list of the name, and that name has been used if any cyclone form. If any name has used, then future that name will not repeat. And also, if once name has used, then they will take the name from another country. So if you Google, easily you can get the upcoming cyclone name. Like next cyclone, if any cyclone form in the North Indian Ocean, India will give the name. That name is Gati. So next cyclone name will be Gati. Now coming to the, we know that the tropical cyclone at surface at anti-clockwise rotating wind. Why it is anti-clockwise? It is because of the Coriolis force. Coriolis force is due to Earth rotation on its axis. It release a force that is called the Coriolis force. That Coriolis force in northern hemisphere, it pulls the wind right direction, and southern hemisphere it pulls the wind in left direction. If you look at this picture, if any low pressure form, wind start moving from high pressure to low pressure. That is the tendency. So this produces the pressure gradient force. We know that any circulating body, Coriolis force act. So these Coriolis force is always perpendicular to the pressure gradient force, and in northern hemisphere right direction. So if air is moving from high to pressure, this is the pressure gradient force and this is the Coriolis force. Resulting path will be like this, and the wind is here, the resulting path will be like that. So the wind start circulating in anti-clockwise direction. So if the cyclone form, they follow some path. What is the basis to follow the path? This picture shows the general circulation of the wind over the globe. This is the intertropical tropical convergence zone. Between plus minus 13, there is a subtropical high. There wind moves from east to west in both the hemisphere. If you go further, there is a subtropical low, then wind starts from high to low and it is west to east. So if cyclone any low pressure form and it converted into tropical cyclone, under the influence of this easterly wind, it start moving westward direction. If you go further if you increase latitude, the Coriolis force come into the picture, and Coriolis force try to pull that wind into the right direction and then start moving to poleward movement. That is called the poleward movement. It means northward. And if again further that cyclone will move under the influence of westerly, it will move in eastward direction. So this is the some general path of tropical cyclone. Another word is landfall. What is the landfall? Everybody is knowing that landfall, but sometimes what is happening if any cyclone comes enter into the land after being over water, people are thinking if some cloud inside the land means landfall has happened, but it is not like that. We cannot call landfall of the tropical cyclone until unless the eye of the cyclone at the coast. In this picture, upper and lower panel of the picture, if you see lower panel of the picture, the eye of the are away from the coast, but most of the portion of the cyclone inside the land. But we cannot tell tropical cyclone has made a landfall. Upper panel, if you see upper panel picture, here the eye of the cyclone over the coast means cyclone has made the landfall. So there is some impact of the tropical cyclone because the tropical cyclone is associated with strong wind, storm surge, heavy rainfall. So due to strong wind, the damage of the structure like houses can be destructed, loss of power and communication, loss of life. Due to storm surge, there is a flooding and vegetation and crop destruction. If any associated storm surge is high, then there is a flooding in coastal area, erosion of beaches, loss of soil fertility, loss of life, and damage of structure. Due to heavy rainfall, there is flooding also, loss of life, vegetation, destruction of the vegetation and crops, contamination of water supply, land subsidence, flooding of the land area. Part of the tropical cyclone. The prediction of the tropical cyclone is not just the track prediction. It consists of many parameter prediction. Like if any tropical cyclone form from initial stage itself start the prediction. The cyclogenesis means the formation of the tropical cyclone. That prediction also very important. Then if cyclone has formed, then we start tracking. So we do the track prediction. When we are giving the track prediction, most important is how much intensity, what is the wind speed. That is the major killing factor when it hits the coast. So intensity forecast is also very important thing. Landfall prediction, very accurate landfall also is very important to evacuate the people within a time. And if landfall happen, then how much the storm surge? And due to storm surge, how much damage has been happened, or that how much damage would occur due to the storm surge. So all prediction is required. So what is the observation over the tropical cyclone? There are mainly 5 type observations to which we monitor the tropical cyclone. First one is the ship measurement. They used to take the ship measurement like SST, wind information, salinity of the ocean. Another is the buoy instrument. buoy measurement. Buoy is the instrument that installed into the ocean and give the SST and salinity information, and along with that wind speed and direction at the height of 10 meters. Then land-based observation like radar and AWS instrument. Another one is aircraft measurement. How much important aircraft measurement in last previous speaker has detailed discussed about the aircraft measurement, because in India usually we don't have the aircraft observation, but US they used to do the aircraft observation when the any tropical cyclone form. And last one is the satellite. That is the most important, because if any tropical cyclone form, they spend more life in the ocean. In ocean, above all four measurement is very less. So that time that satellite plays a very important role to monitor and track the tropical cyclone. So ISRO has launched so many meteorological satellite. First dedicated meteorological satellite Kalpana 1 has launched in 2002. That gave the information about the cloud motion vector. Cloud motion vector is also wind. It computed from the cloud movement, outgoing long wave radiation and rainfall. Then after that, in 2003, they launched the INSET 3A. That was also gave the very important information about the weather. And in continuation INSET series, they launched the INSET 3D and 3DR in 2013 and 2016. In 2013 and 16, in INSET 3D, there is a 6 imager channel and 90 sounder channel, includes 18 infrared channel and 1 visual sounder channel. And another one is the OceanSat. OceanSat giving the information about the ocean, but about the ocean color, what is the wind near the ocean surface. So OceanSat satellite is more important during the tropical cyclone, because this OceanSat 1 and 2 is not operational. ISRO has launched its 1 satellite in 2016 that is operational and giving the very important information about the ocean. What is the function of the SCAT-SAT? This is the scatterometer satellite. It gives the scatterometer observations. It is the active sensor. It passes over the ocean surface, because ocean surface is rough due to wind. Due to wind, there is a wave that is called the capillary wave. And if active sensors send the pulses over ocean surface, it reflected back. If roughness is more, strongly it will reflect. If roughness is low, the wind is low. So based on this principle, the sensor sends the ocean surface information and in the form of sigma naught, and then it converted into the wind speed and wind direction. And one more important meteorological satellite also launched, that is called the megatropics. Megatropics mainly giving the information about the temperature and humidity over the tropical region. So how we can identify the tropical cyclone using the satellite imagery? Mainly 3 type image we have from the satellite: infrared image, visual image, and water image. How infrared channel works? Infrared channel sense the energy as a heat. solar radiation when fall on the Earth's surface, half of the solar radiation absorbed by the Earth, and the absorption capacity for the cloud and atmosphere is less as compared to the Earth. All the absorbed radiation they remit as energy, and that energy that infrared channel sense. So because cloud, if high cloud, the energy is very less, so it appears as a cool as compared to the Earth surface temperature. So IR images shows the temperature of the cloud top. IR sensor cannot take the measurement below the cloud, so it gives the information about the cloud top. They shows the deep organized convection characteristic of the tropical cyclone. This image also not only shows the tropical cyclone location, but can be used to estimate the intensity, because each cloud has certain characteristic and particular wind speed. Based on that wind speed, they can easily identify. If there is snow in the atmosphere, it can easily differentiate, because if it is snow, what they do, they take the number of pictures, like every 15 minutes or every 13 minutes picture, and used to analyze, because snow cannot move, but cloud will move. So based on that, they can differentiate in cloud if it is snow or cloud. Another is visual channel. Observation shows the high value of reflectivity, because if the Earth radiation fall on the Earth surface, it reflected back the radiation, and that radiation sensed by the visual channel. Visual sensor is required the sunlight. So due to that, this is the main disadvantage of the visual channel, is it cannot give the information during the night time. However, the infrared channel can give day and night both information, because it sends the energy. And coming to the water vapor observation indicate how much moisture is present in upper troposphere. It is useful for indicating whether rain is possible or not. So all these sensors used to launch with the geostationary platform, because geostationary platform is at the height of 36,000 kilometers above the equator, and it can continuously monitor over the same area within the 15-minute or 30-minute time interval. So the movement of the tropical cyclone in each minute we can monitor. So here is some animation. If I think it is not working, so can I show in my computer? So this is the IR channel based on the observation during the cyclone. This is not in Indian Ocean cyclone. Very beautifully, that eye wall and outer part has detected by the IR sensor. But if you look at this picture, in visible channel, the movement of the tropical cyclone is appear like black and white, and the center of the tropical cyclone, how accurately you can monitor. So based on this sensor, our NSAT 3D also have the same type sensor, IR, visible and water vapor channel. Based on that sensor, we used to track the tropical cyclone when any tropical cyclone form over the Indian Ocean. This is the IR, visible and water vapor channel. Here you can see this is the during Amphan cyclone, how it appears in the image. You can see in visible channel during the night time there is no observation, but daytime it is giving bright, that tropical cyclone showing as a bright. And this water vapor channel is giving the information about the water content available in the atmosphere. So based on satellite observation, we used to track the tropical cyclone. INSAT 3D and 3DR, two geostationary satellite we have. So it is giving the information every 15-minute interval. So based on that, we can easily monitor the tropical cyclone track. SCATSAT observations also we have. Based on SCATSAT wind, we can detect the center of the tropical cyclone, because this is SCATSAT satellite is the polar satellite. Polar satellite, in this picture you can see it moves pole to pole and giving the information over the each time it gives the different area information. So it will give the information like past type. So this SCATSAT is polar satellite. It gives the information over same area twice in a day. Only two passes are available in same area. This is the megatropics observation. Based on megatropics observation, we can find out the it is giving the brightness temperature value over the tropical cyclone. This is the microwave sensor, megatropic Saphir. Actually, satellite carries so many sensors, and each sensor has some different frequency depending upon the mission goal. So different frequencies sense the object within that wavelength, and the wavelength, based on wavelength, we can categorize this sensor is giving what information. So in that megatropics, that is a microwave sensor that is giving the temperature and humidity profile. So based on this, we can easily monitor the tropical cyclone.
Sorry, sir, I'm
this is
interrupting. Just a minute, interrupting. We are actually running out of time. Can you please finish it within 5 minutes? Sorry.
Okay.
Sorry, sir, for that.
So this is the Saphir observations for funny cyclone. So this is the some algorithm developed by the Space Application Center scientists to predict the tropical cyclone track. So this is the algorithm flow chart. We are not going to discuss in detail this chart, but how they are using this algorithm is based on the wind pattern matching index. So using this, how they are matching, they have made a database using the past SCATSAT observation, and using that algorithm, this way they are matching, where they are matching at each grid point. If the matching index is found greater than 0.6, that point is considered the tropical cyclone center. So in this way, they track the tropical cyclone. Using that algorithm, they have predicted the cyclogenesis of Amphan and Nisarg cyclone in this year in Arabia. So this wind pattern matching index event, this Amphan cyclone has formed on 20th May 12 UTC. This observation event has detected the cyclogenesis of the tropical cyclone in 40 hours before. It is 15 May observation. So 40 hours before, we able to tell this low pressure system has potential to develop into the tropical cyclone. So using the INSET 3D IR channel, we are predicting the center of the tropical cyclone also, because in IR channel, brightness temperature shows less as compared to the environmental temperature over the cyclone area. So using that brightness temperature value, we can easily detect the center, how accurately we can find. Intensity estimation using the satellite observation, there is the only way that is called the advanced Deverock technique to estimate the wind intensity. It is based on the structure of the tropical cyclone in the image. They are considered only main 4 pattern: curve bed pattern, shear pattern, center dense overcast, and eye pattern. Based on that pattern, they have already assigned the T number. That, like, if curve pattern is there, T number is 1.0 to 4.5, and that T number, they have assigned the wind speed value, like maximum wind speed. If T number is 1, then wind speed is like 25 knots. If T number is 8, wind speed is around 170 knots. If you convert, you have to multiply by 1.85, convert into the kilometer per hour, this knots value. And that this for tropical cyclone prediction, we use the Lagrangian advection. A new model has been developed for tropical cyclone prediction that is based on the steering flow. During my PhD, I work on that model and developed this algorithm to track the model. Based on the steering flow, we can accurately predict the track of the tropical cyclone. So in real time also, that model are being used to predict the track. During the Amphan, this is the track based on the 17th May, because the tropical cyclone has made a landfall on 20th. Before 3 days ago, we are able to predict the landfall position accurately using this model. This is the observed and forecasted position of by the IMD. We can see how accurately matching the landfall position. This forecast is based on the 20th May. So I am doing some study using WRF model also. This is some forecast for Fani cyclone based on the 1st May. This is the observed track, and this is the forecasted wind field. You can see how accurately the cyclone movement is captured by the model, even the landfall position of. And this is some forecast of Amphan cyclone. You can see the movement. This is the 6-hourly wind field. So every 6 hours, we can track the center of the tropical cyclone. This is the track forecast based on 18th May. This is the observed track. Very accurately, we are able to give the landfall position of the cyclone. Storm surge forecast also scientists are doing. This forecast is available on Mosaic site. You can see this forecast is based on 17th May. 3 days before, they are able to predict the storm surge height. IMD has shown that, IMD has observed that the storm surge during the landfall is about 4.6 meter. So this model is able to capture that height. You can see. This is the site where you can get the real-time information about the tropical cyclone center, track, intensity information. Archive is also there, and surge forecast. So I would like to conclude here and end up my presentation. Thank you.
Thank you, sir, for your very informative presentation. I'm really sorry for interrupting your lecture, but we have to. Now, I will request Dr. Debaduti Mitra for conducting the interactive session. Debaduti, over to you. Debaduti, are you there? Okay.
Yes, yes. Am I audible?
Yes, yes, you are.
Yes, yes.
Oh, okay, okay. Thank you, ma'am. Thank you, Dr. Singh, for your for such an interesting and engrossing session. Now we have few questions from our participants. So, sir, shall I read out the questions? Sir? Sir, shall I read out the question, sir?
Yes, you can.
Okay, sir. Okay, the first question is from Dr. S.K. Dash. He is asking why the Bay of Bengal is called the hotbed of tropical cyclones. Why the Bay of Bengal
What are
is
you?
called?
Which actually your hot? Why is the Bay of Bengal is hot?
Yes, hotbed of tropical cyclone.
No, I already told, because Bay of Bengal received more rainfall. Due to rainfall, there is a fresh water flux is more in Bay of Bengal region, and the number of river is more, which is draining the water, fresh water, into the Bay of Bengal. So due to that, there is fresh water flux is more, salinity is less. So due to fresh water flux, SST is high. Due to SST, if SST is high, then it is more warmer.
Thank you, sir. Okay, now our next question comes from Professor Alo Guho. She is asking that, as to naming of tropical cyclones, does it mean that a storm with a name that begins with A, like Amphan, is the first storm to occur in the year?
No. Actually, the naming of the cyclone is not based on alphabetically. It is random, but it is based on some meaningful name like flower or any animal or foods. It is not based on the alphabetically or based on any male or female. It is random number, and it is decided by the neighborhood country, that is the 13 member in that WMO, World Meteorological Organization, that they decide what is the name of the tropical cyclone. That is not alphabetically.
Okay, sir. Now, next question asked by Dr. S.K. Dash again. His question is, how tropical cyclone can be monitored by RS at night?
Remote sensing.
Remote sensing, yes, remote sensing at night.
No, dude, I have shown that we have mainly three type of observation: infrared, water vapor, and visible channel. So visible channel is required sunlight. So during night time, sunlight is not there. So that time, IR channel works. IR channel is the functioning based on they sense the energy as a heat. So during the night time also, the earth and atmosphere both remit the energy, and that energy is sensed by the IR channel. So infrared channel is more useful during the night time.
Okay. Now, due to time constraints, the next question will be the last. Now, it is also asked by Dr. S.K. Dash. His question is, what is the distance between the polar satellite and the Earth?
The difference between polar satellite and geostationary satellite.
Yes, sir.
Difference between polar satellite and geostationary satellite.
Yes.
Actually, the geostationary satellite is launched at the height of 36,000 kilometers from the equator, and polar satellite is launched at the height of 700 to 800 kilometers. Okay. So the Geostationary satellite is stationary. Its movement is relative to the Earth motion. So it continuously can monitor same place throughout the time. But the polar satellite, it moves pole to pole. So each time the area is different. So that is the main difference. And the polar satellite gives the information, same area information, only 2 times in a day. But the geostationary satellite can continuously give the information.
Thank you, sir. Thank you, sir, for the lucid explanation. That was indeed a wonderful session.
Thank you.
Now our interactive session is over. So I am requesting Alo ma'am.
Yes, I'm
Alo
there.
ma'am. Yes, ma'am. So you can give the vote of thanks and complete the webinar.
Okay, thank you, Devaduti. Dear participants, we now come to the end of our webinar. We extend our heartfelt thanks to our Honorable Principal Dr. Ashok Mukhopadhyay for his guidance and support, to our respected Administrator Dr. Ashish Ghosh for his encouragement. We offer our sincere thanks to a distinguished speaker, Dr. Scott A. Brown, Dr. Sugata Hajra, and Dr. Sandeep Kumar Singh for sharing so much valuable knowledge with us, for their insightful presentations. We thank our dear colleagues, the entire Seth Anandram Jaipuria family, for their warm wishes and motivation. We thank the members of the Internal Quality Assurance Cell for their constant cooperation and guidance. This webinar would not have been possible. Thank you, members of the organizing committee and technical assistance team, for your support and guidance. We extend our sincere thanks to the wonderful audience for bearing with us during the technical glitches and actively participating in a webinar and making it a memorable one. It was a pleasure and honor having all of you here. We hereby conclude this webinar by wishing everyone a safe, healthy, happy times ahead. Thank you all.